Professor, good morning.
Yes, sir.
Professor, good morning.
Sir.
Ah,
Good morning,
yes,
sir.
Yes, sir.
We welcome our Honorable former Vice Chancellor and Professor of Anna University, Dr. R.Velraj sir, was the inaugural address of the AICT sponsored 6 days ATAL online FDP program. The dates for this program are 27th January to 1st February, 6 p.m. to 9 p.m. The topic of the FDP is energy and electrical vehicles in India, opportunities, challenges, and futures. At this juncture, our Honorable Secretary Sir is on another official meeting. He will join later. And about our college was started in the year 2001 by the IIET Society. At present, we do have 7 undergraduate courses and 4 postgraduate courses. And we do have the NBA accreditation for all the eligible courses and NAC with A grade up to 2027. For this inaugural address, we have invited Dr. R.Velraj, Professor and former Vice Chancellor of Anna University, Chennai. Professor is in the authority in the field of energy, and he is working in the Anna University, and he has more than 40 years of vast experience. And in short notice, Professor is going to deliver the inaugural address. For this ATAL FDP program, at present, more than 217 participants has been registered, and all the registered participants has been approved. And this end of this FDP program, every day Google Sheet is being given to all the participants, and this can be treated as attendance for them. And also they have to give the session 1 and session 2 feedback of the various speakers on each and every day. This attendance is mandatory, and as per the ATAL online FDP program, 80% attendance is compulsory and 60% marks are mandatory. And any doubts and clarification, participants are welcome to clarify with the speaker at the end of their speech. And also the recorded video also will be given to all the participants after completion of the all 6-day program. This topic is energy and electrical vehicles is a vibrant and need of our topic. And in the 6 long day, we are going to discuss about the various opportunities, various challenges at present what we are facing. And also we are going to discuss about the what is the future of the energy in India and also the electrical vehicles future. And the various leading experts from all over India has been invited, and all the experts have been accepted for the presentation. And also the 2 leading industrial experts also accepted for the presentation. Today, after the inaugural speech, a person, Ashok Kumar Elluswamy from Tesla USA, is going to address as an industrial expert of this energy and electrical vehicles in India. Now, I invite our honorable and respected former Vice Chancellor and Professor of Energy Studies at Anna University, Chennai, to propose the inaugural address of this AICTE ATAL online FDP program. Professor, please.
Thank you, Professor Saravanan.
Thank you, sir. Thank you, sir.
On behalf of Dr.
Welcome you,
Saravanan,
sir.
I also welcome all the participants who have come for this AICTE sponsored 6 days ATAL online FDP program on energy and electric vehicles in India, opportunities, challenges, and futures. Definitely, it's a very good title, need of the hour. Everyone, hope many participants from many departments it's an interdisciplinary field. Definitely, the participants must be from various disciplines. In the coming years, only multidisciplinary, transdisciplinary people only can do some challenging work, novel work, any innovative work, only they can do. So definitely this platform, this online FDP will be helpful to understand about the interdisciplinary subject about energy and electric vehicle. Being an energy expert in this field for several years, I want to give the scenario. What is the energy scenario in this country? Why this electric vehicle became very much important in the recent years? That way you must be knowing this, but still I want to give the scenario, past and present scenario in the energy, so that how important this electric vehicle in the near future you can understand. Energy, we have been using this energy since several years, 2-3 centuries. We have been using energy aggressively, particularly from fossil fuels. We have been generating energy. This energy generation, because of fossil fuel usage, the environment got degraded in the last 200 years. That we have realized only in the last 2 decades. After the invent of electricity, we started using electricity for various applications, and also the fossil fuels for mobility, vehicles application. I think there is a small disturbance. I request all the participants to mute your link. Otherwise, there will be a small disturbance. Yes. So this energy and environment are opposite in nature. That one should know. Energy and environment are opposite in nature. When we use energy, it is possible to utilize the energy at the cost of degrading the surrounding. This thermodynamically or law of nature itself says, when we do something, we may make perfection in a small system, but it is possible at the cost of more disorder in the surrounding. That is why when we started using this energy for the last 2 decades, last 2 centuries, though the life comfort, our human life comfort is increasing, environment got disastered. You all must be knowing the carbon dioxide level in the atmosphere. At the time of evolution of the earth, it was only 65 ppm at the time of evolution of the earth. Till we started using energy aggressively in this earth, that is before 2 centuries, after several millions of years, it became only, it reached 165 ppm only, parts per million. 165 ppm, from 65 ppm, that is increase of 100 ppm over millions of years. But when we started using this energy in the last 2 centuries, this 165 ppm became 365 ppm in 2000. That means on an average 1 ppm increase over every every year from 1800 to 2000. But in the last 2 decades, okay, more now it is 25 years. In the last 25 years, the carbon dioxide level reached now 420 ppm. From 365 to 420 ppm, it reached within 25 years. It means nearly 2 ppm increase is happening presently. This is because the large population is there in 2 countries only in the world, China and India. These countries' growth is very high in the last 2 to 3 decades. The energy usage is increasing appreciably in these 2 countries, means the major population of the world, 40% of the world population is there in 2 countries. Their lifestyle increases means the energy utilization is also very high. Hence, the environmental disorder is very, very high. So now we have realized In the last 2 decades only, we have realized, not only we realized, the whole world realized that using fossil fuel is very dangerous in the near future. So the whole world now made a lot of policies to utilize the renewable energy in a great way. Most of the countries now they have made a mandatory measures to use the solar energy and other renewable energies in their total energy consumption. In many countries, they have made policies before 2030 or 2040, they should their renewable energy share should be 80% of the total energy power generation. So that share people have made. India also has made lot of mandatory measures. When our country made the solar energy mission, Jawaharlal Nehru solar mission in the year 2010. Before 2010, in this country, the total power generation from solar was only less than 1 megawatt. But when the country made a decision to promote solar energy in the year 2010, immediately the solar power generation started increasing. 2010, the earlier government made a policy to generate 20,000 megawatt by 2023. But within few years, the Gujarat and Rajasthan had performed well. They started their power generation through solar increased appreciably after 2010. Then the next government, present Prime Minister, after he took charge in 2014, he revised the measure of the policy mandatory target of 20,000 megawatt by 2023 to 1 lakh megawatt by 2023. But now we have almost achieved nearly now 96,000 megawatt we are generating from solar. We should appreciate our present Prime Minister's vision of making that solar power generation. In 2014 itself, he revised the target of Jawaharlal Nehru mission from 20,000 megawatt to 1 lakh megawatt. Now we have, because of this corona pandemic, there is a small decrease in the target. Otherwise, we would have exceeded the target. But now it is revised in another 7 years, in another 6 years, we should achieve 5 lakh megawatt. Now it is nearing 1,96,000 megawatt. Now our country has revised the target of 5 lakh megawatt through solar by 2030. That means the growth possible for the next 6 years is tremendous. The solar potential is very, very high. Why the solar energy potential is very high? Not only for power generation we are going to use, for vehicle also. The major power, earlier the power generation, the major power consumption in 2 sectors, one is power sector and the vehicle sector, transportation sector. In the transportation sector, we haven't converted this fossil fuel sources of energy into electrical energy. We have changed only to mechanical power, and that mechanical power is utilized. But now the trend is to avoid the pollution. The trend is towards electric vehicle. So energy to electric vehicle. So why all these years this renewable sources was not considered by the human? Because it is highly intermittent in nature. The electrical energy generation, once it is generated, immediately we need to use that energy. But solar energy, it is not a continuous source of energy. So when the sun shines only for 10 hours in some countries. Okay, in poles, if you see, it is for 6 months, it is available continuously, and 6 months it may not be available. But in most of the countries, it may, in summer season, it may available between some 10 hours to 14 hours. Most of the countries where this northern poles, northern equators. So another 12 to 14 hours, the sun energy is not available. That is why all these years we have not bothered about the solar energy, since as it was intermittent in nature. But now we are forced to use the solar energy to safeguard this environment. So now to utilize these intermittent sources of energy, another technology is required that is also growing in a faster way. That is the energy storage. So now to utilize the solar energy effectively, you need energy storage. Now the whole world has given lot of importance and spent lot of money and in R&D to promote energy storage technologies. Because the countries invested money in R&D for solar, the solar energy now became cheaper than the conventional sources of energy. Now the investment required to generate 1 megawatt power is less than the power money fund required through coal-based power plant. Coal-based power plant, it may be more than 4.5 crores. Now, for a solar-based power plant, for 1 megawatt, the investment required is less than 4.5 crores. That is around 3.5 to 4 crores. Maybe place to place, it may vary a little bit. Now, if the storage technology is also become popular and inexpensive, and if you are able to make it cheaper, then the ultimate source of energy is the solar for all our applications. Then we can also stop converting fuel to mechanical power to drive the vehicle. Electrical energy itself we can use for all our requirement, and also for transportation sector it will become successful. Already the government all the governments started promoting electrical vehicles in a big way. Electrical vehicles. Now the three things research is required. Solar energy already became very popular. The next technology is energy storage. Now all the lead acid from the lead acid battery to all different kinds of storage devices are becoming popular. I'm sure in the coming days, the investment cost on storage also is going to be lesser. Then all our applications, the solar energy is the only provision. I also want to tell this electric vehicles now, lot of you don't think that electric vehicle has attained the matured stage. No, it is. If we start working on this, if R&D investment is very high on our electric vehicle, definitely the cost will become much cheaper than this, much lesser than even the conventional kind of vehicles. It is possible. So all the discipline, the people who are in electrical, mechanical, chemical, and all physics, chemistry, all these people should come forward to contribute in the research and development in the electric vehicles and energy storage that will promote this electric vehicle in a large way, and by making this investment cost for electric vehicle very less. And I want to tell all the participants here, if you start working on electrical vehicle, definitely the innovation possibility will be very high. If 2 or 3 different discipline people started working together, lot of innovations are possible, and how to produce high torque with it by varying the motor. For initial torque should be higher, and then it should operate at the lower torque. How it is possible with the electric motor? And if you start thinking, there are a lot of new developments are possible, and the battery storage and the design modification to take care of. When we keep this battery very heavy material or battery in the vehicle, the stability should be there, where it should be kept, and the opportunities are very high for the design and the new materials and manufacturing side and the electric motor innovations and optimization. Lot of opportunities are there for the researchers to make innovations in the near future. Since I have train at 7:20, so I'm stopping. Though I have another 5 minutes, I'm stopping here. I will come for one more session on Friday or Saturday. Definitely, I will whatever knowledge I have in this field, I will share with you during the next session. I thank Dr. Saravanan for the opportunity and wish you all the best. And I am sure that all the participants who are participating in this AICT sponsored ATAL FDP. You will get lot of information from various experts. Wish you all the best. And I once again convey my wishes to the organizers and also the participants for the successful learning of this electric vehicle and energy opportunities, challenges, and future. Thank you. I take leave of. Thank you,
Thank
sir.
you very much, Professor, for giving insights and your broad knowledge and depth knowledge for the various participants through this inaugural address. I know that in spite of your busy schedule, you have accepted our invitation and coming in online in this ATAL FDP. On behalf of AIGT, on behalf of ATAL, on behalf of our own institute, on my own behalf, we extend our heartfelt thanks from our core of the heart for delivering the inaugural address. Thank you very much, Professor.
Thank you. Thank you.
The 6 long day, we are going to cover the following various topics in this FDP. The thing is current landscape electrical vehicles in India, cost-effective solutions for mass EV adoption, government policies and incentives for EV adoption, recent advancement in battery, design of electrical vehicle, renewable energy integration with electrical mobility, electric vehicle manufacturing opportunities for India, advancement and impact of electric vehicles on India in energy grid, role of startups in India, EV ecosystem, consumer perception and acceptance of EVs, battery technology and recycling technologies, sustainable and carbon footprint reduction through EVs, challenges in rural electrification for EV infrastructure. All these various topics are going to be covered in the forthcoming days. I request all the participants to be present in online and until the end of the session up to 9 p.m. and also give their attendance and also give the daily feedback. Next, it is my pleasant duty to give the industrial experts introduction. The first industrial expert is going to deliver the industrial address is none other than Mr. Ashok Kumar Elluswamy. He is a vice president in Autopilot and AI software at Tesla, San Francisco Bay Area, USA. Basically, coming to the education qualification of Mr. Ashok Kumar, he has been graduated in College of Engineering, Gindi, Anna University, Chennai, in the branch of Electronics and Communication Engineering from the year 2005 to 2009. Later, he has completed his MS at Carnegie Mellon University at US in the field of robotic system development from 2012 to 2013. Coming to his experience in his field, he done his research intern in Volkswagen Electric Research Lab from May 2013 to December 2013. And after that, he worked in a software engineer in the Webco vehicle control systems. He is in full time from April 2010 to July 2012 in Chennai in the area of vehicle dynamics and control. Without taking much of the time, I invite Mr. Ashok Kumar Elluswamy from Tesla to propose his industrial talk. Right now, he is working in Vice President in AI software. Welcome, Mr. Ashok Kumar Elluswamy, sir.
Hey, everyone. Thanks for inviting me. Mr. Saravanan, my name is Ashok. As you mentioned, I work at Tesla on AI software, mainly for self-driving. I prepared this presentation earlier about how self-driving works and things like those, but I think today I'm not fully aware of the audience, to be honest. I've been informed that it's people working on, or professors working on electric vehicles. But I think maybe what I want to talk about today is more than just electric vehicles in some sense. The entire world is on the precipice of artificial superintelligence, and we are on a rapidly rising exponential with a very high exponent, and we have 4 to 8 years left before we have widespread robots in various different domains, including cars driving by themselves, autonomous robots serving people in their homes, and various functions that are typically done by humans, including software, other kind of like control for electrical and electronic things, for example, chip design, what have you. If you can produce the training data for it and come up with an objective for the AI to solve it, the algorithms that are being developed nowadays are quite capable and can solve them. So I personally think that we have 4 to 8 years left to achieve artificial superintelligence, where the AI is smarter than any individual on Earth on any topic. Some say I'm conservative, others say I'm too aggressive in my timelines, but nonetheless, I think it's a matter of if, not when, and it is happening within our generation for sure, for my generation at least. So that's sort of what I want to talk about today. And I think the session is for 1.5 hours. I don't think I have 1.5 hours to like talk about the entire thing, but I could speak my mind on these topics for 15 minutes or something, and then we could have some Q&A session, or you can interrupt me any time, just ask me questions, and we can just discuss about this. And then there's some past presentations that Mr. Saravanan has and we could watch them if you want more technical details about any particular development. But I think the information that are in these presentations could be a bit outdated in some sense that AI is developing so rapidly. Like every week, the pace of AI progress is insane, and it's just hard to keep up overall. Maybe to give a brief history of how this is happening to everyone, if they're not aware of it. Many of you might actually be aware of it. Nonetheless, I can sort of phrase my view of how this is happening. There's AI algorithms that have been in the works since the 1970s. But then in 2000, all of 2000s and then early 2010s, on 2012, for example, for image detection task, for example, if there's an image or video, and if you ask the AI to identify trees or chairs or what have you, it might have an accuracy of 50% or something, some very low number like that. But then in 2012, Ilya Sutskever and Alex Krzyzewski launched this paper that sort of shot that performance from 50% accuracy roughly to 73% in 2012 from University of Toronto, and that shook sort of the research environment into using neural networks for machine learning and computer vision. And that result was so stunning that people started throwing out the old algorithms, started working on neural networks. And since then, we have been on an exponential path to just make progress. And then the main breakthrough that happened in 2012 was actually not even the neural network invention. The neural network algorithms have been present for more than 40-50 years even before that. The main breakthrough that happened in 2012 was actually just that the algorithms the neural network was scaled up to use GPUs from NVIDIA. And back then, the previous ones were implementations that were in MATLAB running on CPU, which the scale was never sufficient to sort of fit the data. And 2012 is when the GPUs were able to be scaled up. Using GPUs, the neural networks were able to be scaled up to fit the data, and that's why it started working well. So since then, people have been extending the architectures and making work for more and more tasks. Excuse me. And after that, every year there was like new inventions. In 2017, the transformers architecture was invented, where like for machine translation, translating from one language to a different language. The previous approaches, usually the convolutional neural networks are mainly for image processing, for language processing. The LSTMs were LSTMs and RNNs were like the state of the art, so to speak, back then. But then the performance was still quite poor. But in 2017, the transformers architectures were invented as a sequence-to-sequence translation problem, where you can give a sentence in French and ask it for in English or what have you, and then so it took like a big sequence of inputs, and then emitted a big sequence of outputs. And sort of the transformers architecture, just like how in 2012 the scaled up convolutional neural network architectures bet the baseline heavily, the transformers also were crazily leapfrogging the previous RNNs and LSTMs, mainly because the LSTMs and RNNs were sort of like a sequential architecture where they would, predict one token, put it back in next, and so on. So at training time, it was very slow to train and learn things. And these GPUs are hungry for data and like want to learn, but we need to like reduce the compute time and reduce any bottlenecks in learning. So the transformers architecture is a parallel architecture where it can simultaneously learn from all the inputs, and training is extremely fast. Even the inference is could be still a bit slow, but then training is extremely fast. So it's able to absorb and learn from a lot more data, and that made it much more scalable for learning, arbitrary sequences. Even though it was invented for machine translation, and the same technology was just extended to predict what the future is going to be, in terms of next word prediction or something like that. So what Shorter wrote as like just a translation where given some language sequence and produce a different language sequence, the same transformers were given like a past sequence predict the future sequence, and when rolled out in this fashion, when it's predicting just the next word, it is able to learn extremely useful things about the world, because in order to predict the next token accurately, you need to have a compressed model of how the world works. You can, there's like this famous phrase like the cat jumped over the fox or something like that, and then like it doesn't like not to like remember the sentence, like it just needs to like have this in its memory, and then you can like when you say the cat jumped over the dash, and it can fill in the details of it. It's typically it's the word fox or like a few words like that, but it's not a refrigerator, for example. Like those kinds of like discriminative knowledge is baked into the weights of the neural networks, and by just like trying to predict this next token, the models are capable of like incredible intelligence. And once you have this sort of like base model that's pre-trained on the entire internet, then you can sort of like apply reinforcement learning on top of it to achieve various more advanced tasks. So that's the main breakthrough after 2017. And what people figured out after that, from 17 until 2025, essentially is that you can just keep scaling up these neural networks, and then they just work better. You don't need any new algorithms for the most part. I mean, there are algorithm improvements here and there, but for the most part, people are finding that if you just scale it up, train it sufficiently long with lots of data, it just gets better. And on top of it, if you apply reinforcement learning for the proper objectives, it's getting way better, even for the same scale of pre-training. And the same technique applies not just for next word prediction of text. It can also work for images, videos, control actions. So you can use the same thing for robotics. At Tesla, we moved to a so-called end-to-end driving stack. So the last couple of years ago, where the car can drive itself. Currently still it's supervised, but then it can see videos around the car and then take actions around what is the correct control action to take, such that the car drives safely and smoothly and gets there fast. And that sort of end-to-end approach bet the previous rule-based approaches by many orders of magnitude, and it is continuing to improve also. and we expect the progression to continue, provided we scale it up, scale the data, scale the models, and so on. And why is this important for the energy revolution and so on? It sort of like goes together because these neural networks are quite large. And since they need to be quite large to work well, it does take a lot of energy to train and infer this. But then like they allow for these robots to be incredibly capable. So electric vehicles, currently the main competitor for electric vehicles is not other electric vehicle that are being manufactured. Those are not the competitors. The actual competitor is personally owned vehicles that are just gas powered, and not to like beat the cost of the gas powered vehicle. The electric vehicles have to be way cheaper because there's a huge barrier to like cross the threshold of where more people can afford electric vehicles over gasoline vehicles. Just because like there'll be 100 years of innovation on gasoline vehicles and only like maybe 10-20 years of innovation on electric vehicles. But then the big boost to that is going to come when the cars can drive themselves, where for the same amount of capital invested to produce a car, the car can produce 5 to 10x the value, because most of the time the cars are just idle right now. When people buy cars, they drive for 1 or 2 hours a day. For the most part, most people drive for 1 or 2 hours a day, and then for the remaining 22 hours of the day, the car is idle. And it produces a lot of money to produce a car. So if the car cost is like $25,000 or $50,000, then and it is such an expensive asset, and for most people it is the second most expensive asset that they own. And after spending so much money on this asset, it is only being used for a small fraction of its lifetime. And that's an incredible waste of resources. You need to produce a lot of metal and other elements, pay a lot of people to produce a car. In the end, it's only being used some amount of time, and you can usually increase the use from 2 hours per day to 10 to 20 hours per day if the cars can drive themselves and didn't require a human to operate them. And so that's sort of like why the by going to this AI and robotics future, we make transportation extremely affordable for everyone. And that's sort of like what Tesla's mission is, and that's sort of what I'm working on. And that should help the rapid adoption of electric vehicles, not just for Tesla's sake or something, for the entire world to transition to sustainable energy module. That's sort of like quite an accelerant, so much more so than any other innovation in the mechanical design or the chemical design of the batteries or what have you. In the short term, in the next 4 to 5 years, self-driving cars are the biggest improvement to electric vehicles. And I think the technology that we're developing right now can work not just in the US, but also globally, including India. I'm from India, and I know how driving is in India, and I'm pretty confident that it can work in India also. So that's sort of my spiel. If you have any questions, I'm happy to answer.
Participants, please, any queries, please clarify with the speaker.
No one has any questions? Is this one question? How does it take video and process
Take
it?
video and process it.
Yeah, in the vehicles that are manufactured by Tesla nowadays, they have 7 to 8 cameras depending on the model year. And then there's a giant neural network that runs in the car based on a computer that's designed also by Tesla, that's inside the car, that takes the live video of these 8 cameras, and then in real time understands the things around the car. You can like sort of like see um, uh, um, around the car, and it can drive itself. I'm not sure if many people have actually watched videos of it driving itself. Maybe I can just share my screen and then sort of show a video of driving itself. You guys see my screen? I hope you can see my screen. So this is sort of like you can just turn it on, and you can like lane changes. You can just like get in the car, type in an address, and press start, and you can just do all of the driving itself. Right now, it's still in the supervised phase where, in the rare case that it makes a mistake, the person has to take over. But then we are working on not requiring a person to do any takeovers. Can run like a lot of like interesting scenes. Obviously, it's not like driving in India right now, but I'm pretty sure it can. They can do like these kind of high-speed left turns, respond to cutting in vehicles. And pull over at the end of the trip. Please share videos of EV 360-degree image caption, please. Okay. I guess like you can find a lot of videos of Tesla driving on YouTube, for example, if that's helpful. I'm not sure if that's what you refer to. If you're asking for the dataset, I'm pretty sure we cannot release the dataset. In Indian traffic scenario, is it possible to implement? Yeah, Mr. Karthikeyan, yeah, I'm pretty sure that we can implement in Indian traffic scenarios too. The neural networks learn from how to drive based on how humans drive. So as long as you're getting training data from India, and you add that to the neural network and the AI to learn, I'm pretty sure it can learn Indian rules or the lack thereof. But still, there are not like super hardcore rules in India, but then you still have some basic fundamentals, like, you can't collide into someone, you can't like sort of go and drive in super scary fashion. Those kind of like implicit rules of the road will be respected. And any explicit rules can also be respected. It's just a matter of what training data you collect. Guess if there are no other questions, then that's it from me. Thank you so much. Thank you for welcoming me. Thank you.
Dear participants, is there any queries? Ashok sir?
Yeah. Hi.
Ashok sir, if no queries, shall we move on to the video session, sir?
Sure. Yeah, you can play the AI video, especially the self-driving section could be quite useful. But there's also like other videos there where we talk about like chip design and other robotic innovations.
Sir, Mr. Ashok sir,
Yeah.
it is a Thanksgiving session on behalf of our All India Council of Technical Education, New Delhi, under ATAL FDP scheme, and from our own management and my own behalf, we thank you very much for participating and giving the industrial inaugural session for this 6-day long ATAL online FDP program. Literally, we have disturbed you in the early morning.
No, it's
because
okay.
they-
Yeah, it was just I just wanted to make sure that that I got the core message, which is that AI super intelligence is coming soon, and as humanity we got to work on it and make sure that it's done safely and it's for the benefit of humanity. That's yeah,
Yes,
that's
sir.
the main
Well said.
message.
Rightly pointed out. Thank you very much as a part of this ATAL FDP program and from industry side. Thank you very much,
Thank
sir.
you. Thank you.
Thank you, sir. Bye.
இதையும் போட வேண்டாம், நான் சொன்னா போடு.
Actually, it is the torso. We have our battery. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one thing. We're also leveraging both our vehicle products and our energy products to roll all of this. So that's streamlined manufacturing, really efficient cooling method, battery management, and also clean. And of course, we can leverage the existing infrastructure and supply chain to make it. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce. We want to leverage both the autopilot hardware and the software. As well as audio support. And then it also has hardware level. Important to protect both the robot and the robot. So now that we have our core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well. But before we do that, I'd like to introduce Malcolm, who's going to speak a little bit about our structural foundation for the robot.
Tesla have the capabilities to analyze highly complex systems. You don't get much more complex than a crash. See here a simulated crash, Model 3, superimposed on top of the actual physical crash. It's actually incredible how accurate it is. Just to give you an idea of the complexity of the model, it includes every nut, bolt, and washer, every spot weld. They have 35 million degrees of freedom. Quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence the robot? Well, we can make a model, and since we have crash software, we use the same software here, we can make it fall down. The purpose of this is to make sure that if it falls down, it doesn't, but it's superficial damage. We don't want to, for example, break the gearbox that it's on. That's equivalent to a dislocated shoulder with a robot. Difficult and expensive to fix. So we wanted to dust itself off, get on with the job, it's convenient. We can also take the same model and we can drive the actuators using the inputs from a previously solved model. Bringing it to life. So this is producing the motions for the tasks we want the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can place in the model. This is showing just simple walking. We can create the stresses in all the components that helps us to optimize the components. These are not dancing robots. These are actually the modal behavior, the first 5 modes of the robot. Typically, when people make robots, they make sure the first mode is up around the top single figure. The reason to do this is to make the controls of walking easier. Very difficult to walk. You can't guarantee where you're walking around. That's okay to make one robot. We also make thousands, maybe millions. We haven't got the luxury of making carbon fiber titanium. We want to make them from plastic. Things are not like this. So we can't have these high targets. I call them dumb targets. We've got to make it work with low targets. Is that going to work? Well, if you think about it, sorry about this, but we're just bags of soggy jelly and bone throbbing. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. We just make the controls harder. So we take the information from this, the modal data, let's feed it into the controls. That allows it to walk. Looking at the knee, we can take some inspiration from biology. Look and see what the mechanical advantage of the knee is. Turns out it actually represents a 4-bar link, quite non-linear. That's not surprising, really, because if you think when you bend your leg down, torque on your knee is much more bent than it is when it's straight. So you'd expect a non-linear function. In fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be scientific. We've played all the tasks through this graph. This is showing walking spot we did in the stress. And that's the torque seat of the knee against the knee bend on the horizontal axis. This is showing the requirement for the knee to do all these tasks. And then put a curve through it, circling over the top of the piece. And that's saying this is what's required to make the robot do these. So if we look at the 4-bar link, that's actually the green curve. And it's saying that the non-linearity of the 4-bar link has actually linearized the characteristic of the force. What that really says is that's lowered the force. That makes the actuator have the lowest possible force, which is the most efficient. We want to burn energy up solid. What's the blue curve? The blue curve is actually, if we didn't have a 4-bar link, we just had an arm sticking out of my leg here with an actuator on it, a simple 2-bar link. That's the best we could do with a simple 2-bar link. And it shows that that would create much more force in the actuator, which would not be efficient. So what's that look like in practice? Well, there's just the very tight package in the knee. See, go transparent in a second. You'll see the 4-bar link there. Operating on the actuator. This is determined the force and the displacement on the actuator. I'll now pass you over to Constantina to tell you a lot more detail about how these actuators are made and designed optimally. Thank you.
Thank you, Marco. So I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. So we are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive side. While the robot that has 28 actuators, it's not obvious what are the tasks at the actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a single point into the cloud. Then We do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize, and we parse our cloud. We parse our cloud again for every joint spec, and the red axis this time denotes the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs, and even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable, we need to be able to reduce the amount of unique actuator designs. Therefore, we run something called commonality study, which we parse our cloud again, looking this time for actuators that simultaneously meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side, angular contact ball bearing, and on the high-speed side, and on the low-speed side, a cross-roller bearing, and the gear train is a strain wave gear. There are 3 integrated sensors here and the bespoke permanent magnet machine. The linear actuator The linear actuator has planetary rollers and an inverted planetary screw as a gear train, which allows efficiency and compaction and durability. So in order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. And I will let you enjoy the video. So our actuator is able to lift a half-ton, 9-foot concert grand piano. And this is a requirement. It's not something nice to have, because our muscles can do the same when they are directly driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our hips for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague Mike, who's going to talk to you about hand design. Thank you very much.
Thanks, Dr. Dinas. So we just saw how powerful a humanoid actuator can be. However, humans are also incredibly dexterous. The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors. It has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hands. The converse there is pretty interesting, because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller
which drives the fingers, and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that we grasp. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand levers. You just heard how we went about designing the Tesla bot hardware. Now I'll hand it off to Lon and our autonomy team to bring this robot to life.
Right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work we've done on Autopilot over the past few years. Most components ported quite easily over to the bot's environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. Another interesting problem to think about is in indoor environments, mostly with that sense of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frame over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. We also did quite some work on the simulation side. And this is literally the Autopilot simulator, to which we've integrated the robot's locomotion code. And this is a video of the motion control code running in the Autopilot simulator, showing the evolution of the robot's walk over time. So as you can see, we started quite slowly in April and started accelerating as we unlock more joints and different more advanced techniques like arms balance over the past few weeks. So locomotion is specifically one component that's very different as we're moving from the car to the bot's environment. So I think it warrants a little bit more depth, and I'd like my colleagues to start talking about this.
Hi everyone, I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And the following, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bot, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then for trajectories that connect these footsteps using toe off and heel stride, just as humans do. And this gives us larger strides and less knee bend for higher efficiency. The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Thank you, Felix. Hello, everyone. My name is Anand. I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens. It takes a couple steps and falls down. Well, that's a little disappointing. But we are missing a few key pieces here, which will make it work. Now, as Felix mentioned, the motion planner is using an idealized version of itself and a version of reality around it. This is not exactly correct. It also expresses its intention through trajectories and wrenches of forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any similar model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planner doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis force, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model. We use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add correction to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We needed to use its hands and arms. Let's talk about manipulation.
Hi everyone, my name is Eric, robotics engineer on Tirupati, and I want to talk about how we use the robot manipulate things. We wanted to manipulate objects while looking as natural as possible and also get there quickly. So what we've done is we've broken this process down into two steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the location of the hands, the elbows, and torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalized for variation. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it reaches the For instance, if the box is in this location, then our optimizer will create this trajectory. Next, Juan's going to talk about what's next for the office. Tesla. Thanks, Derek. Right. So hopefully by now you guys got a good idea of what we've been up to over the past few months. Start having something that's usable, but it's more useful. There's still a long and exciting road ahead of us. I think the first thing within the next few weeks is to get Optimus at least up par with Bumble T, the other bus prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories, and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I was mentioning earlier, indoor navigation, graceful floor management, or even service, all components needed to scale this product up. But I don't know about you, but after seeing what we showed tonight, I'm pretty sure we can get this done within the next few months or years, and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 weeks. Thank you very much. Hey everyone. I am Ashok. I lead the autopilot team alongside Milan. God, it's for me so hard to copy that Optimus section. Still try nonetheless. Anyway, every Tesla that has been built over the last several years, I think has the hardware to make the car drive itself. We have been working on the software to add higher and higher levels of autonomy. This time around last year, we had roughly 2,000 cars driving our FSD beta software. Since then, we have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today. This did not come for free. It came from the sweat and blood of the engineering team over the last 1 year. For example, we trained 75,000 neural network models just last 1 year. That's roughly a model every 8 minutes. Coming out of the team, and then we evaluate them on our clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the tech. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD beta software is quite capable of driving the car. You should be able to navigate from parking lot to parking lot, handling city street driving, stopping for traffic lights and stop signs, negotiating with objects at intersections, taking turns, and so on. All of this comes from the camera streams that go through our neural network that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car. And the planning software drives the car based on that. Today, we'll go into a lot of the components that make up the system. The occupancy network acts as the base geometry layer of the system. This is a multi-camera video neural network. From the images, it predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, walls, whatever it predicts, if it's physically present, it predicts them along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course. But then the roadways have lots of different lanes and they connect in all kinds of ways. So it's actually a really difficult problem for typical computer vision techniques to predict the set of lanes and the connectivities. So we reached all the way into language technologies, then to the state of the art from other domains and not just computer vision to make this task possible. For vehicles, we need the full kinematic state to control for them. All of this directly comes from neural networks. Video streams, raw video streams come into the networks, go through a lot of processing, and then outputs
the full kinematic state, positions, velocities, acceleration, jerk, all of this directly comes out of the networks with minimal post-processing. That's really fascinating to me because how is this even possible? What world do we live in that this magic is possible, that these networks predict fourth derivatives of these positions, and people thought we couldn't even detect these objects. My opinion is that it did not come for free. It required tons of data. So we had to build sophisticated auto labeling system that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks, distill the information into labels that train our in-car neural networks. On top of this, we also use our simulation system to synthetically create images. And since it's a simulation, we trivially have all the labels. All of this goes through a well-oiled data engine pipeline where we first train a baseline model with some data, ship it to the car, see what the failures are. And once we know the failures, we mine the fleet for the cases where it fails, provide the correct labels, and add the data to the training set. This process systematically fixes the issues. And we do this for every task that runs in the car.
Yeah, to train these new massive neural networks, this year we expanded our training infrastructure by roughly 40 to 50%. So that puts us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks and map them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent systems on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we have to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced scheduling code across the full FSD platform.
All of these neural networks running in the car together produce the vector space, which is again the model of the world around the robot, the car. Then the planning system operates on top of this, coming up with trajectories that avoid collisions or smooth, make progress towards the destination using a combination of model-based optimization plus neural network that helps optimize it to be really fast. Today, we are really excited to present progress on all of these areas. We have the engineering leads standing by to come in and explain these various blocks. And these power not just the car, but the same components also run on the Optimus robot that Milan showed earlier. With that, I welcome Padil to start talking about the planning section. Hi all, I'm Padil Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. A lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal lateral profile. Now, obviously, we are being a jerk to the pedestrian and we will spook the pedestrian and its viewpoint. We could have moved forward slowly, sought for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing, stay slow initially, find the reasonable gap, and then finish the maneuver after all the events. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far
because you will miss out on a lot of parallel interaction. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem. It will be close to order of 10 milliseconds, even after a lot of incremental code. Now, for a typical crowded unprotected lift, say you have more than 20 objects, each object having multiple different feature modes, the number of relevant interaction combinations will blow up. The planner needs to make a decision every 50 milliseconds. So how do we solve this in real time? We rely on a framework what we call as interaction search, which is basically a parallelized research over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, the nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting. We use a set of maneuver trajectory candidates to rank over a bunch of interaction decisions, and also incremental goals for a longer horizon move. Let's walk through this research very quickly to get a sense of how it works. We start with a set of vision measurements, namely lanes, occupancy, moving objects. These get represented as fast abstractions as well as gradient features. We use this to create a set of goal candidates. Lanes, again from the lanes network, or unstructured regions which correspond to a probability mask derived from human demonstration. Once we have a bunch of these goal candidates, we create steep trajectories using a combination of classical optimization approaches as well as our network planner, again trained on data from the customer feed. Now, once we get a bunch of these steep trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized. So we branch further onto the option on the right, and that's where we bring in more and more complex interactions, building this optimization problem incrementally with more and more constraints. And the research keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the research. Inside each node, initially we started with creating trajectories using classical optimization approaches, where the constraints like I described would be added incrementally. And this would take close to 1 to 5 milliseconds per action. Now, even though this is a fairly good number, when you want to evaluate more than 100% interactions, this is not scale. So we ended up building lightweight variable networks that we can run in the loop of the planner. These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits. With this, we were able to bring the runtime down to close to 100 microseconds per action. Now, doing this alone is not enough, because you still have this massive research that need to go through, and you need to efficiently tune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis, what is the jerk and axle required for a given maneuver. The customer fleet data plays an important role here again. We run two sets of, again, lightweight variable networks, both really augmenting each other. One of them trained from interventions from the FSD beta fleet, which gives a score on how likely is a given maneuver to result in interventions for the next few seconds. And second, which is purely on human demonstration, human-driven data, giving a score on how close is your given selected action to a human-driven trajectory. The scoring helps us tune the search space, keep branching further on the interactions, and focus the compute on the most promising outcomes. The cool part about this architecture is that it allows us to create a cool blend between data-driven approaches, where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks. Now, a lot of what I described was with respect to the agents we could observe in the scene, but the same framework extends to objects behind occlusions. We use the video feed from 8 cameras to generate the 3D occupancy of the movement. The blue mask here corresponds to the visibility region, we call it. It basically gets blocked at the first occlusion you see in the scene. We consume this visibility mask to generate what we call as ghost objects, as you can see on the top left. Now, if you model the spawn regions and the state transitions of these ghost objects correctly, if you tune your control response as a function of the likelihood, you can extract some really nice human-like behaviors. Now I'll pass it on to Phil to describe more on how we generate this. Thank you.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year. This network is our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. What you will see here is the raw network output from our internal dev tool. The occupancy network takes video streams of all our 8 camera sets input, produces a single unified volumetric occupancy in vector space directly. For every 3D location around our car, it predicts the probability of that location being occupied or not. Since it has video context, it is capable of predicting obstacles that are occluded instantaneously. For each location, it also produces a set of semantics such as curb, car, pedestrian, and road debris, as color-coded here. Occupancy flow is also predicted for motion. Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motion, such as a swerving trainer here. This network is currently running in all Teslas with FSD computers, and it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator. So how does this work? Let's take a look at the architecture. First, we rectify each camera images with a camera calibration. And the images we're showing here were given to the network. It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count image to the network. Since it has 4 bits more information, it has 16 times better dynamic range, as well as reduced latency, since we don't have to run ISP in the loop anymore. We use a set of reckless and biased FPS as a backbone to extract image space features. Next, we construct a set of 3D position queries along with the image space features as keys and values fit into an attention module. The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry to derive motion. Last, the spatial temporal features go through a set of deconvolution to produce the final occupancy and occupancy flow output. They're formed as fixed-size voxel grid, which might not be precise enough for planning and control. In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location. After knowing the model better, let's take a look at another example. Here we have an articulated bus parked on the right side road, highlighted as an L-shaped box here. As we approach, the bus starts to move. The front part turns blue first, indicating the model predicts the front bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated problem for traditional object detection network, as you will have to see whether I'm going to use one cuboid or perhaps two to fit the curvature. But for our occupancy network, since all we care about is the occupancy in the visible space, and we'll be able to model the curvature precisely. Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads. The surface and the voxel gray are not predicted independently. Instead, the voxel gray actually aligns with the surface implicitly. Here, we're at a here press where you can see the 3D geometry of the surface being predicted nicely. Planner can use this information to decide perhaps we to slow down more for the hill press. And as you can also see, the voxel gray aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field for nerves. We're looking into both incorporating some of the nice nerve features into occupancy network training, as well as using our network output as the input state for nerves. As a matter of fact, Ashok is very excited about this. This has been his personal weekend project for a while.
These nerves, because I think the academia is building one of these foundation models for language using like tons of large data sets for language. But I think for vision, nerves are going to provide the foundation models for computer vision because they are grounded in geometry, and geometry gives us a nice way to supervise networks and pieces of the requirements to define an ontology. And the supervision is essentially free because we just have to differentially render these images. So I think in the future, this occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentially rendered into any image that was observed. I personally think is the future of computer vision, and we do some initial work on it right now. But I think in the future, both at Tesla and in academia, we will see that these combination of one-shot prediction of full volumetric occupancy. That's my personal bet. Thanks for showing. Here's an early result of a 3D reconstruction from our fleet data. Instead of focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the work in 3D space for driving. And we want to do this for all our fleet data over the world in all weather and lighting conditions. And obviously, this is a very challenging problem, and we're looking for you guys to help. Finally, the occupancy network is trained with large auto-label data set without any human in the loop. And with that, I'll pass to Kim to talk about what it takes to train this network. Thanks, Phil.
All right, hey everyone. Let's talk about some training infrastructure. So we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips. So we've been looking at the occupancy networks just from Phil. Just Phil's videos, it takes 1.4 billion frames to train that network you just saw. And if you have 100,000 GPUs, it would take 1 hour. But if you have one GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and run 4,000 GPUs for auto labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache.
Let this soft mineral melt in your mouth to rebuild your gums and teeth and never need a dentist again. Did you know there is a natural way to regrow teeth and gums that only 3% of the population even knows?
Helen Hadfield was able to win any competition she took part in. She was known as the contest queen because she had won 7 trips to Paris.
Hello, everyone. Midwest is currently prioritizing the IT route. DA guests, please make your way to our other amazing zones to board your robotaxi experience. Thank you.
Hi, we are t-shirt manufacturers from Tirupati, Tamil Nadu. These are our pure cotton polo pocket t-shirt.
Hello, sir.
So no audible for before few minutes, sir.
Yes, sir.
So no audible before 20 minutes before, sir. No audible, sir. Only video for going, sir.
Yeah, good evening. Are you able to hear me?
Yes, sir.
Okay, yeah.
Yes,
sir.
Sir. Welcome, Professor Dr. Muthu Kumar, sir. I will introduce you, sir.
Yeah, please.
Yes, sir. Very good evening to all the participants. Now this is session 2. Is going to address by the expert lecture by Professor Dr. P. Muthu Kumar, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Tirupati. Professor P. Muthu Kumar received his PhD degree in Mechanical Engineering from IIT Madras in 2005. Earlier to this Tirupati, he has worked in IIT Guwahati. He has got various research fellowships, awards, and excellence. Following are the various awards: DAD Research Fellowships and IEA Young Engineering Award, PACE Fellowship, and MP Baya National Award in 2015, Fellow of Indian Engineers, Fulbright Nehru Academic and Professional Excellence Award in 2018, Mechanical Engineering Design Award by 2017, Eminent Engineer Award in 2019, Innovation Challenge Award in 2020-21, Outstanding Engineering Service to the Country Award by Institution of Engineers, Abdul Kalam Technology Innovation National Fellowship Award in 2021. He has been serving as an editorial board members of several reputed elsewhere journals such as International Journal of Hydrogen Energy, Thermal Sciences and Engineering Process. He has published around 450 research articles in various international journals and conference proceedings. So far, he has edited 4 books and written 16 book chapters. He holds 15 national patents to his credit. He has supervised 35 PhDs, 65 MTech and 10 MS students so far. He has successfully completed 20 sponsored research projects in his. Currently, he is handling 12 research projects. He has been serving as an expert member in several ministries, including DST, MHRD, Ministry of Oil and Natural Gas, Ministry of External Affairs, Government of India for research project funding and monitoring. He is also an expert and steering members for various agencies like BIS, AICTE, NAC, and many other professional organizations. In spite of his busy schedule, Professor Dr. P. Muthu Kumar has accepted our invitation and is going to deliver on the cost-effective solution of the mass EV adoption. And he is going to throw some light on the hydrogen energy and its various applications for energy saving potential in these areas. Without taking much of the time, I invite Professor Dr. Muthu Kumar for delivering his expert address. Please, sir. Welcome you, sir.
Thank you. Thank you, Saranan, for your kind introduction. And good evening to all. I think people have joined across India, I guess. This
Yes,
is
sir.
online. Being online, this is another advantage. So we can connect people across the world. And in
Yes,
fact,
sir.
often I used to also deliver lectures from, to other countries as well. Anyway, this is the thanks to COVID. So COVID has, provided us the several other opportunities to explore. So without taking much time, so I will go into the subject. Anyway, this topic is slightly away from the EV, but though they have some kind of interlink, now the EV, of course, goes in two modes. One is the battery, everyone knows it's a battery. And then if you see the long-term sustainability of this solution, it may be kind of a question mark. So maybe in around 2030, so both technology, one is the fuel cell-based technology, another is a battery-based technology, both the technology will emerge. And eventually by 2000, in the countries like in India, by 2035, the hydrogen is going to play a major role, not only in transport sector, but also in domestic and industrial and many other sector. So though, this hydrogen is going to play a major role in the transport sector, I thought of course, addressing, the importance of hydrogen energy and how it can be produced. And in production, I'm not going to store much, but the major challenges like the storage and the other related application, then maybe the purification and compression. These are the some of the potential application. I feel so maybe thought of giving some introduction about this technology. And maybe if the time permits, since there are many are of course the young researchers, and there are I guess there are few PhD scholar as well. So for their career perspective, maybe I wanted to maybe throw some light about the various opportunities available and maybe the various funding agencies, so that some of the young faculty can explore the project funding. Okay, so I'm going to cover all these aspects. So let us go into the the presentation. Give me a moment. So my screen is visible now. My presentation is visible, Dr. Saravanan?
Yes,
No,
sir.
Professor,
Yes, sir.
it is
Yes,
not.
sir. Yes, sir.
Now, hello, Professor.
It's visible?
No, sir, it is not visible, sir.
It's not visible.
Yes, sir.
Okay, then wait a minute. Let me check again.
1 second, sir.
Maybe can you check again?
Now also it's not visible, sir.
Okay.
Sir, can we share it from here, sir? No, it is not. It will be.
Okay, 1 minute, 1 minute. Just a moment.
Yeah.
Just
Yes, sir. Yes, sir. No problem.
So this, I think you have to give some option. Have you given the option for me to share the screen?
Yes, sir. Yes, sir. Option is there, sir. It is given.
But usually I do it, but it's.
need a presentation mode. In down presentation mode.
Present பண்ணா ஒரு ஸ்லைடு மாத்த முடியாதுல்ல?
Let me check. I think it should be done. I used to make presentation, lot of presentation only now only.
Yeah, I know, Professor. I know.
It's okay. Text. Not able to see. Okay, so Saravanan, so what I will do, I will quickly, it's there already there in the WhatsApp. Okay, I will share you this file. Can you open it from your side? Anyway, I don't want to waste time. I can also do it
sir.
on laptop.
Yeah, we will open it, sir. Please
Yeah.
do, sir.
Yeah, 1 minute. I'm sharing it. So I have done it. Can you open it from your side?
Yes, sir. We will open it, sir. Wait
Yeah.
a minute, sir.
Anyway, I'm also trying from here. In the meantime, I shared the complete file to your WhatsApp. Just check it. I think some issues there here. Their screen. You got it?
It's getting open, sir, because file is very large in size.
It's a 4400 AMP.
Yes, sir. Halfway through, sir. Wait a minute, sir. Wait a
Maybe we
minute.
can also, so the participants are mostly from, the faculties, or you also having the research scholars as well?
Sir, majority faculty, sir, more than 217 participants registered.
Oh, that's really great. So they all are from which discipline?
Majority from mechanical, sir, and minor from electrical branch.
Okay.
So far, 141 participants are in online.
Oh, great. That's really great. Okay.
Other branch faculties and student research scholar also registered out of their own interest because they want to know the energy and EV vehicles, sir.
Okay, fine.
That
So
is
I
the
think
scenario about this.
check it. I think you got it. Just check.
Yes.
Yeah, I think you got it.
Sir, please check.
This is the earlier also I have done it through this one, and I don't know this I think there is some issue, in the settings from your side. This setting, this is an Apple system.
We enabled everything, sir.
Huh?
We enabled everything here, sir. No issues for us, sir.
Okay. Anyway, I don't want to waste the time. Anyway, I'll make it. I'll set it. Yeah. Just you can please you can open the file from your side.
Yes, sir. We are opening, sir. Participants, please be on the line. There is a technical issue. We will resolve it. Sure. Professor?
Yeah. Okay, fine. Thank you very much.
Okay, Professor.
Yeah. So you made it in presentation mode?
Yes, sir.
Okay. Very good. Anyway, thank you. So sorry for the, this inconvenience.
Professor, no problem, Professor. It is a technical issue, sir. Nothing from your side.
Okay, fine. Yeah. Okay. So thank you. So well said now. Yeah.
Yes.
Okay. So as I already mentioned, so the topic is slightly into the hydrogen energy. So in this topic, so I will talk about little bit first beginning to little bit about the energy scenario in India or maybe in the world. And then we can also talk a little bit about the importance of hydrogen energy. Then the to make the hydrogen energy into the commercial market, we will see the challenges, of course, the various challenges. And the main challenges is the storage and you can say the transportation. So we talk more about the storage and transportation. Then maybe also the associated, the applications like the purification and compression. So we will discuss, and maybe time permits, and then maybe I will also talk a little bit about the career guidance of the young researchers, and then maybe the key area of can say the some of the core engineering areas where you can pursue your future career, or maybe the research, and then some of the funding agency in general. Okay, then maybe I will leave maybe about 10-15 minutes for the interaction. Okay, this is about the overall summary of my talk. Yeah, please go to the next slide. So everyone knows about the Sustainable Development Goals. This is more important. So most of the developing nation and developed nation committed to achieve, these 17 Sustainable Development Goals. So India also committed to achieve. If you look at the goals, for example, the poverty, no hunger, and healthy lives, education, and gender equality, providing potable water, sanitation, economic growth, and etc. There are about 17 sustainable goals. Among these 17 sustainable goals, the goal number 7. Can you go back to this one? The goal number 7, that is the providing clean and affordable energy. So if you have clean and affordable energy, then only you can achieve the remaining 17 sustainable development goals. So therefore, across the world and most of the nations given commitment towards the providing clean and affordable energy to their 100% population by 2030. India also committed to provide clean and affordable energy to our 100% population by 2030. Okay, next. So next one. Next. Yeah. So if you see this one, let us see the basic human needs. So we need food. So to maintain our metabolism, we need food. Without food, of course, we cannot maintain our metabolism. And we need shelter and cloth. For making shelter and cloth, we need energy. Without that, we cannot make. Even without energy, we cannot, cook the food also. And for getting the purified and potable water, we need energy. Without energy, you cannot get purified water. So the scenario, it may so happen, maybe in future that you have to spend energy for getting purified oxygen. Even the scenario has already happened during winter, particularly the region which is nearer to Delhi. Of course, the pollution level goes above 450, 450 to 460 ppm level, particularly CO2. This mainly because of the the burning of too much of agriculture waste nearby region. So there are many oxygen pollers. They often for a couple of months, and they'll where you can get the purified oxygen. If the same scenario continues, we will end up with the same kind of issue. So therefore, for meeting all basic human needs, we need energy. Without energy, we cannot sustain. When I talk about this sustainable energy, it should be deliverable. You can go back. It will deliverable at any point of time, and the price should be reasonably cheap, and it should be the availability should be abundant. These are the key requirement of an energy. And so here, this is very interesting factor here. Till 13% of the world population do not have access to the electricity. Okay, and this is very funny. Even India also, nearly about 20% of our population do not have access to the electricity. Anyway, we are committed to provide electricity to every household item by 2030. And again, another alarming picture is nearly 35 to 40% of world population do not have access to the clean cooking fuel. So the sustainable goal number 7, which includes both the cooking energy as well as the household energy requirement. Okay. So as a result, even in India itself, nearly every year we are losing about 3 to 4 lakh people are dying, mainly because of improper cooking practice. This is another concern. So therefore, our government of India is committed to provide 100% electricity. Electricity to 100% population. Similarly, we also committed to provide the cooking fuel to our 100% population. So there are many schemes being, of course, done. And not only India, even many of the countries, they were, of course, exploring the various options to provide clean cooking fuel to their 100% population. Okay, next. So if you look at the energy, our requirement, then still 86% of our crude oil we are getting imported from the other countries. And for this, we are spending nearly about 50% of our revenue for the importing the coal and the crude oil. So therefore, by 2030, our government is committed to reduce the crude oil import by about 15%. Okay, and similarly, LPG also we are importing nearly 50% of our requirement. So this also need to be, of course, cut down. So if you see, because of their economic reform and the living improvement in the lifestyle of the people, our energy requirement is increasing at a rate of about 7 to 8% per year. At the same time, we also need to reduce the crude oil import. See, the only solution is we need to, of course, transform our energy, the present hydrocarbon-based energy economy into the renewable-based energy economy. Then only it is possible. Okay, go to next. So if this is the current energy scenario. So right now we have nearly about this roughly about you look at this. Can you go back to the previous one? Yeah. So yeah, fine. So currently we have about next one. Nearly about 450 you can say the 450 gigawatts of power, and majority of the power we are nearly about 54% of power we are getting from the coal-fired thermal power station, and renewable is roughly about you can see the 10.5 plus 13.3, that is roughly about 43.5%. This is from the renewables. That is the the hydro and as well as the other renewable energy, which includes which comes under the renewable energy umbrella. So this number is slightly better compared to the world average. But however, we are committed to produce. We are committed to provide another about 100 gigawatts of renewable energy power by 2030. This majority is coming from the solar PV. So when you go for such a huge amount of renewables, and the storage will be the challenge. I mean, the reliability is the challenge. The from solar PV you can generate energy during daytime, and similarly wind and the hydro also available only particular season. It won't be available throughout the year. And so therefore, if you transform your hydrocarbon, the current hydrocarbon based energy economy into the renewable energy based energy economy, so you will end up with having kind of instability. Okay, because these are not kind of the continue, you cannot get continuous supply. They are most of the renewables are intermittent nature. So then what is the solution? Okay, go to next. So again, you see here, this is the potential of the renewable energy and as well as the finite energy. So the coal will be maybe available for another 300 odd years, and uranium, of course, infinitely available. Gas also maybe another 150 odd years it will be available. But coming to look at this potential, the solar, which is almost 23, so 1 terawatt hour. Basically, the maybe in 2050, the requirement of energy will be about 28 terawatt hour. And if you see this one, the energy, the amount of energy available in the solar, that is nearly about 23,000 times higher the times of the terawatt hour. That may be many times more. Maybe you can say few thousand times higher than the the present energy requirement. So therefore, even if you whatever the energy which is captured by the earth, solar energy captured by the earth, out of that, if you convert maybe 1 or 2% the energy, that may be more than sufficient for our future energy requirement. So that much potential we have. Similarly, we also have huge potential in the wind and hydro as well. Go to the previous one. So if you see this three, the forms of, can you go to the previous one? Previous slide. Yeah. No. Previous. Yeah. So here, the maybe if you look at these three, the energy sources like the fossil. So here maybe availability maybe about 300 years, particularly coal, and the safety is very high and the cost is moderate. But the issue is that CO2 emission. That's the penalty which you have to pay for it. And coming to the nuclear, again, it is availability is abundant, okay, unlimited, and the cost is again the moderate. Safety is high, but here, the main here issue is that waste disposal. Okay, as per the technology concerned, it's very safe. But the question is how we are going to handle the waste. That's a big question mark, but it's a highly controversial subject, which I don't want to get into that. But now the more interestingly, now come to the renewables. renewables again, as long as the universe exists, you will have the solar, I mean the renewables. And safety is very high because here there is no moving parts, nothing. It's absolutely carbon-free technology. But if you see the cost, which is much lower than the cost of your cost of electricity which you are generating from the conventional coal-fired thermal power station. So therefore, everything seems to be much better, attractive, and that's the reason now this technology is, particularly the solar PV and associated technology, is picking up, and it's having the exponential growth in the recent times. Go to next. Yeah, so here you can see the kind of the prediction of three forms of fuel like solid, liquid, and gas. Solid is already reached its saturation, and its now source is depleting slowly, maybe by 2050. And maybe it may be a question mark in extracting, and there are several issues associated with the solid fuel. Similarly, liquid fuel also. And again in future, maybe right now, of course, we are extracting only 20% of the conventional crude oil. Still we have 80%. But thing is, to extract the 80% of the conventional crude oil, you have to spend a lot of energy, which may not be a sustainable solution. So that's the reason its usage, and as well as its kind of exploration, it's declining, and maybe around 2050, all the gaseous fuel will come into the picture. Maybe associated with the electrical battery and all this technology. Among all these gaseous fuel, the hydrogen is going to deserve its major attention, mainly because of its environmental friendliness and high energy content, and the abundant I mean, it's abundant. Almost 90% of the universe is made up of hydrogen, because it's not exactly the hydrogen gas, but it's hydrogen is found in the combination of the other kind of a hydrocarbon. So the abundance is huge abundance. So because of all these reasons, this is going to play a major role in the future. Okay, go to next. So now, if you see this one, maybe in the 18th century, we started, the energy from the wood, and then we slowly transformed into coal, where the number of carbon atoms per hydrogen atoms got reduced from 10 to 2. And then slowly we moved to oil, where the number of carbon atoms further reduced to 0.5. And then maybe gas, maybe you can say around gas means all the CNG, compressed natural gas, and producer gas, and all this type of the gas, and which has only 0.2, 25, you can say, the carbon atoms per hydrogen atoms. And eventually we are going to end up with hydrogen, which is free from carbon. So that's how the the decarbonization, of course, carbon neutral or maybe decarbonization trend, of course, going to achieve. Okay, go to next. So the so basically, coming to the hydrogen, basically hydrogen is a diatomic molecule. It's a H2. In gases, it is always available in molecule forms, which has no color, no odor, and no taste, and it's a flammable and non-corrosive, non-toxic. It possesses all the good characteristics of the fuel, and it's diffused very fast, and the burning velocity is also very high, and it has if you see look at this I mean, you can see the flammability range, which is very high. There are several features, but usually hydrogen will be hydrogen will be available in 3 isotopes, and protium you have 1 proton on 1 electron. Then in a deuterium, that is, we have the 1 proton on 1 electron and 1 neutron, because in case of the protium there is no neutron. And then the third one is tritium. You have, of course, the 1 proton, 2 neutrons, and 1 electrons. So basically, the conventionally, the hydrogen is available in the form of protium. Maybe certain laboratory condition you can make deuterium, but tritium is extremely difficult to make this isotope, which of course usually it is used for R&D purpose. Okay, go to next. Okay, so if you see the property, the flammability range of hydrogen is 4 to 75% in volume. If you have the mixture where the hydrogen is present from in terms of volume, it is occupies say from 4 to 75%, it will form a combustible mixture. And the ignition energy of hydrogen is very less in comparison with other fuel. And the auto ignition temperature also, hydrogen is little high. Okay, this makes hydrogen kind of good fuel, because hydrogen by itself it won't combust. For combusting hydrogen, you need to have external kind of agent. That is, in a way, it's good. and flame speed is very high, and then chromatic density, that is the one issue, serious issue, because hydrogen is a very light gas. Its density is about 0.082 kg per meter cube. Suppose if you want to store 1 kg of hydrogen, you need roughly about 11 meter cube per volume. That's the only issue. Nevertheless, we see its calorific value, which is almost 3 times higher than the conventional fuel, and the diffusivity in hydrogen is almost 4 times higher than the petrol and methanol. These are the other desirable properties which make hydrogen as an ideal fuel. Okay, go to next. And so the triple point of hydrogen is roughly about, you can say, the 13.8 Kelvin, and critical point is 33.2 Kelvin. That is above which you cannot condense the hydrogen. And melting point available at 14 Kelvin. These are the other characteristics. Usually hydrogen boil, the boiling point of hydrogen, you can say liquefaction temperature of hydrogen is 20 Kelvin. So if you want to convert hydrogen into liquid, so you have to cool the entire gas below 20 Kelvin so that you can get the hydrogen. Okay, and so this, of course, most of you are aware of it. And next, so now if you see next, yeah. So the use of hydrogen, of course, you have unlimited application. You name any application, you can find the hydrogen. For example, hydrogen is going to be used as a fuel and as well as the energy vector in transportation sector. And in maybe after 2030, it is mandated that the steel industry and ceramic industry has to use hydrogen, and it is also going to play a major role in the cement industry as well. And even the many air company, like for example Airbus, is trying to explore the use of hydrogen, and then the ship in the marine industry, they are going to use hydrogen, not in the form of hydrogen, they are going to use in the form of ammonia. Like for example ammonia, methanol, these all are the energy vectors of hydrogen. And hydrogen is going to be used as a kind of a feedstock, or maybe the fuel for heating application and cooking application. Their hydrogen is going to use. So India is having many such programs. I'm going to explain you at the end of the talk. Go to next. So if you look at this, for example, if you produce hydrogen from water, anyway, that is the primary kind of a feedstock, and you can use any one of the primary sources. For example, you can use sun or wind, or maybe even you can use the nuclear energy also. So through the electrolysis, you can generate hydrogen. This hydrogen can be used as a fuel, or maybe the kind of the energy, you can say the energy carrier for many applications, including transportation, this aviation and residential, commercial, and industrial. So at the end of the once you use the hydrogen, whether in the form of fuel, whether in fuel cell or the combustion device or the furnace or maybe any chemical process, at the end you will be getting water as a the end product. So the cycle is starting from water and ending at water, and the water produced at the end of the cycle can be taken to the production point, and it can be produced. So maybe look at the cycle here. The hydrogen is acting as an energy carrier for transforming the energy available in the form of renewables, the renewable source, to the user point. Okay, just like electricity. Okay, so in this cycle, nothing is taken from the environment or given back to the environment. Okay, next. So now you can see here, this is the more clear illustration. The first cycle, this is the present hydrocarbon-based energy economy. Here, what we are doing now, during the transportation of the fossil fuel, or processing of the fossil fuel, or storage of the fossil fuel, we are polluting the land, water, and air, and everything we are polluting. And during the combustion, that is when you combust the fossil fuel, we are taking green oxygen from the environment. Then we are giving back all the harmful emissions such as CO2, NOx, SOx, and etc. As a result, the environment is getting polluted day by day. Then coming to the hydrogen-based energy economy, if you produce hydrogen from the renewables, you can take water as a feedstock and electrolysis, and then you will be getting oxygen as a byproduct, which you leave to the environment and take the hydrogen to the user. And during combustion, whatever the amount of oxygen which is emitted during the hydrogen generation process, the same amount will be taken from the environment, and you can combust the hydrogen. And so when the hydrogen get combusted with oxygen, then you will get your end product as a water vapor. So exactly, this water vapor is the same amount which you have taken from the the environment during the production. So therefore, the cycle is absolutely complete. Okay, and nothing is taken from the environment, as I told earlier, and it's also released from the environment. So basically here hydrogen is acting as an energy carrier for transforming the energy available in the form of renewable source to the user. Okay, nothing else. Next. Okay, so if you see this calorific value, as I told you, the higher calorific value of hydrogen is about 142 megajoules per kg of hydrogen. So which is higher than, which is almost 3.5 times higher than the diesel, gasoline, petrol, and methane, and etc. So in terms of energy, hydrogen is having more advantage. Okay, go to the next. Only thing is, you will have the this it's a less dense. That's the only issue. Okay, go to next. So from the renewable sources, hydrogen can be produced, from number of ways. For example, the using electricity generated from the geothermal, the wind and hydro, or even from the solar photovoltaic or solar CSP. And this electricity can be used for electrolysing the water. You can produce the hydrogen. And now the electrolysis, this is becoming very kind of this one. At present, the cost of production from the electrolysis little expensive, maybe about $4 to $5 per kg. But however, maybe in about another down the line, by 2035, our target to reach $2 per kg. Okay, and so the hydrogen also can be produced from the biomass, which is the cheapest option now. So then roughly now the cost of production is roughly about $3 per kg. And then there are other processes, for example, electrochemical process, or the the electrochemical process. Here the heat can be used for spilting the water. So all this process, for example, the electrolysis, where the electricity generated from the renewable is completely designated as a green hydrogen, and similarly the biomass gasification also, you can say it's designated as a green hydrogen. Even the photolysis also, you can say, when you obtain heat from the sun, and if you do the spill the water, then it can be also treated as a green hydrogen. So in the hydrogen based energy economy, we need to address 4 pillars like hydrogen production, storage, and transport and distribution, and end use. So right now we have mature technology for end use. For example, you can use hydrogen as a feedstock or fuel or energy vector for many applications, including domestic industry, marine, and aviation, and you name any application. So we have a lot of application, and even production also. Now the research is being actually it's going on in the electrolysis, and that is the one process where across the globe we are looking for, and we are now trying to produce the cheaper electrode and the cheaper kind of membrane for the electrolysis process, and we are also trying to minimize the so-called all the losses associated with the hydrogen, which includes the activation losses and the pyrolysis losses, and then the ohmic losses. These are the losses we are trying to address, so that the energy requirement for the electrolysis can match close with the theoretical value, that is, which is roughly about 1.4 volt. But currently, for producing 1 mole of hydrogen, the required voltage will be roughly about 2.2 to 2.4, depends on the process. So anyway, this many kind of breakthrough is coming in this direction. Maybe eventually by 2030, maybe 2032, we will achieve our target of generating hydrogen by about $2 per kg. So another is the hydrogen storage. Here is the major bottleneck. So as I told you, for storing hydrogen, it's a really challenging. The reason is that you cannot store hydrogen in the form of gas because it's very light. If you want to store 1 kg of hydrogen at atmospheric pressure and temperature, you need to have about 11 meter cube of volume. That is practically impossible. Even if you want to store in the form of liquid, you have to bring the temperature down to 20 Kelvin. That is minus 253 degrees Celsius. Again, storing hydrogen at minus 253 degrees Celsius will be extremely difficult. You need to have a thick-walled vessels and many things. And so now there are several options being, of course, explored. So that's why now people are talking about storing hydrogen in the form of ammonia or methanol or some other hydrogen-based energy vector. Anyway, eventually we will find some solution. The distribution, of course, you can transport hydrogen through the tube trailers, and you can transport hydrogen through the pipelines, and you can also transport hydrogen in the form of liquid, cryogenic liquid, or maybe the cryo-compressor form. There are many options. Okay, we will see. Go to next. Yeah, 1 minute. So hopefully I'm going in a proper flow, or I'm going very fast. Professor Saravanan? Hello? Yeah, anyone can respond. Audience?
Sir, okay, sir. Okay, no issues.
Okay, so
Sir,
I'm
it's
going.
going smooth, sir.
Sir, okay,
Okay.
okay, sir. Okay, sir. Okay.
Yeah, I also need to have some feedback from the audience. Okay. Okay. So
Yes.
they are coming to the.
Comfortable screen, sir.
Okay, thank you. So if you want to store hydrogen in the form of gas, you have to pressurize up to about 800 bar. That is the type 3 or type 4 cylinders. But this,
Sorry to disturb Dr. Muthu Kumar, sir.
yeah.
Sir, everything going smooth. I am here only.
Okay, okay, thank you. Okay, fine.
Okay, Professor. Okay, Professor.
So if you want to store hydrogen in the form of gas, you have to pressurize up to about 700, 800 bar. That is using type you can store using type 3 or type 4 tank. Usually now these tanks are very, very expensive. India, we are not producing it, but now even we don't have testing facilities also. But now we are planning to set up such testing facilities in India through part of the Hydrogen Valley program, but it will take some time. And even the storage of hydrogen in the form of liquid, that is also a challenge. We have to spend roughly about 30% of the energy only for storing the hydrogen, liquefying the hydrogen. Remaining, we'll have only 65% left out. Again, storing the hydrogen for a longer, in the form of liquid for a longer period will be very difficult. So the reason is that since the temperature difference, your ambient is available at 300 Kelvin, your hydrogen is stored at minus 253. If you see the temperature difference, which is roughly about 280, so 253 plus maybe if you say 30, that is 280 Kelvin approximately. It's a very huge, the temperature difference. So because of this much temperature difference, and even if you have the, maybe the heat leak of about 0.001 watt, and the hydrogen started, the boil, and inside the system the pressure will build up, and once the pressure exceeds the critical its design limit, then there will be a pressure relief valve which automatically opens and releases the hydrogen. This is called boil-off loss. So typically the amount of hydrogen wasted, get released from the system due to the boil-off loss will be roughly about 3 to 5% of volume. That means if you store it for about 20 days, at the end of the 20 days, nothing will be available in the tank. Okay, this is a serious challenge. Therefore, these two options are not practically viable now. However, now in the development of the low cost, you can say the composite cylinder, that is it's becoming kind of attractive now. Researchers across the globe, they are started working. So India also, there are few researchers started working on the development of type 4 tank. Maybe eventually, if you get the kind of a cost-effective solution, then the storage issue can be addressed. Okay, next. So the another interesting form of storing hydrogen is you can store hydrogen in the form of solid. Okay, how you can store it? See, there are kind of the metals like the lanthanum nickel alloy, that is LaNa5 alloy, and ZrMnFe, zirconium manganese ferrous based alloy, and TiFe, the titanium ferrous alloy. These are the alloys they are found to absorb hydrogen. Okay, when you expose these alloy in presence of hydrogen, so these hydrogen, of course, these metals, basically alloys. Okay, alloys absorb hydrogen. So when you expose hydrogen in presence of these materials, what happens? The hydrogen molecule will stick over the surface. Since the hydrogen molecules has two atoms, and once it stick over the surface, that's called chemisorption. Then the molecules will break into the atoms. Then these atoms will diffuse into the metal lattice. Okay, it will diffuse, and once it reaches the the center of the metal, the atom, the nucleus of the metal atoms, it will try to form a kind of a hydride phase. Okay, that is called nucleation and growth. Okay, so then after that, the alloy will transform into the hydride form. The metal hydride, the alloy, intermetallic alloy will transform into the hydride form, and where the hydrogen will be stored. Once the hydrogen atom reaches its the nucleus of the metal lattice, and it will make a strong bond. The hydrogen makes a strong bond between the two metal atoms. Then the hydrogen will be stored in the form of solid. Okay. Then how do you retrieve back? So whenever you need hydrogen, what you got to do? So during this absorption of hydrogen by the metal hydride is an exothermic reaction. That means when it makes the bond between the two metal atoms, it releases the heat. Okay, this is called, this heat will be in the range of about 15 to 75 kilojoules for every mole of hydrogen. Okay, this is a huge amount. So this heat can be rejected anywhere between the atmospheric temperature up to about 500 degrees Celsius, depends on the material composition. So when you want to get back the hydrogen, you have to supply the heat. So this heat, the temperature at which the heat supplied to the system can be minus 30 degrees Celsius to plus 500 degrees Celsius. That means when you are trying to supply heat in the minus, below the ambient, that means what? You are producing the cooling effect. Okay, so you are producing the cooling effect. So this is called endothermic reaction. This endothermic reaction temperature can be varied from minus 30 to plus, of course, 200, 300 degrees Celsius. Depends on the material composition. Okay, so so this technology is very safe. But the only thing is, it's since the weight of the the alloy. For example, if you take the the PIFE, this density is about 8,000 kg per meter cube. So that means the weight of the host material will be very heavy. Say, for example, if you take 1 kg of this alloy, it can store, depends on the configuration, it can store nearly about 14 grams of hydrogen up to about 65 grams of hydrogen. Okay, so depends on the metal composition, this it will range. But still it is, for example, if you want to store, higher amount of hydrogen, you have to go with the magnesium-based hydride. The magnesium-based hydride, though they were little light, but they operate at high temperature, above 250 degrees Celsius. That's another challenge. But however, the low temperature alloy, for example, lanthanum, titanium, nickel, the zirconium, all this alloy can absorb maximum about 12 to 20 grams of hydrogen per kg of alloy. But still it is beneficial. Okay, go to next. Okay, so this is the typical, you can say the thermodynamics of formation. For example, when you look at this, the figure, you have the x-axis, you got the logarithmic of pressure, and y-axis, you got, sorry, the, the x-axis, you have the hydrogen concentration that is given, and then the y-axis, you have the logarithmic of pressure, ln of P. And, you see these are the kind of red color line, this is called the isotherm, okay, isotherm, constant temperature process. So when you apply, when the supply pressure goes above a particular threshold value, then only the material started absorbing the hydrogen. During the absorption process, the pressure remains constant. The pressure inside the system remains constant. That means whatever the hydrogen you are supplying to the metals, the metal alloys, it goes inside the metal lattice. That means the system pressure remains constant. Still, it maintains the constant pressure till it reaches the its maximum saturation. Saturation means once all the interstitial portions are filled with the hydrogen atoms, the alloy won't absorb any more hydrogen further. Then after that, if we further supply of hydrogen, increase only the system pressure. That's why the pressure, of course, goes little high. Okay. So the region where the pressure is constant, that is called plateau region. This width of this region represents the amount of hydrogen stored. Okay. Go to next. So, so here is again a simple illustration. For example, if you want to go with the pressurized storage, say about 200 bar pressure, so the size of the vessel will be bigger than your car. Okay, then liquid also slightly the capacity will reduce, size, the volume will reduce slightly, considerably, but still it's a sufficient size. Then you can see here the first and second option, these are the metal hydrides. The solid state storage, you can see the size of the tank. Okay. So in terms of volume, this is competitive, very, very competitive, but weight only the issue. Say, for example, suppose if you want to store hydrogen for fuel cell technology for any industrial application, where the weight is not a criteria, then this could be the best option. Okay, for stationary application, where the weight you are not you don't need to worry about the weight for the stationary application. Anyway, the system is going to place on the floor. There won't be an issue. The issue will come only in case of the transport application. Okay, yeah. Go to next. So basically the B, of course, at IIT Guwahati. Earlier I was at IIT Guwahati, and for last 3 years I'm working here at IIT Tirupati. In both the institute, we have developed many the metal hydride based, you can say the system for hydrogen compression and hydrogen storage and hydrogen purification and cooling and heating also. For all this application, so the fabrication of the reactor is the very crucial things. Basically, the absorption of hydrogen by the metal hydride or desorption of hydrogen from the metal hydride, both are heat-driven mass transfer phenomena because they were in basically they are exo or endothermic nature. But I mean, it's heat transfer associated with the mass transfer. So you have to design the reactors considering the heat and mass transfer, the characteristics. And for optimizing the heat and mass transfer characteristics, we developed several thermal models, and based on the thermal models, we explored different reactor geometry. Then we have optimized this reactor geometry again with the help of the models. And then after that, based on the optimum configuration, we have fabricated, and these fabricated reactors are, of course, tested for various applications. Okay, go to next. So now I am going to illustrate you some of the practical, you can say the systems. So mostly the system will be like this. It's a kind of shell and tube kind of exchanger, heat exchanger. You can see here the tubes. There's a white color one. These are the tubes, and through which the cooling fluid will be supplied during absorption process. That means because during absorption the heat is released, so you have to remove the heat. And during desorption process, you got to supply the heat. Okay, so through which through the cooling tubes, you can supply the heating and cooling fluid. And the center one, that is where the yellow color arrows are given. So this is basically, it's a filter through which during absorption you can supply the hydrogen, and during desorption the hydrogen will come out from this one. Okay, and the gray color one are these are the metal hydride powder which will be filled. Okay, go to next. So here the number of tubes and orientation of the tubes, everything will be optimized. Are optimized based on the thermal models. Now you can see here the various systems which we have developed, and many of these technologies already transformed to the industry for the commercialization. And we are also now developing the large scale system for fuel cell, and even for the transportation, and then the hydrogen compression application. Many such systems are going to come in maybe in 1 or 2 years. So the first one is basically it's a system. It is fabricated for hydrogen storage and purification. Whatever the system you are storing here, you can store nearly about 11,000 meter cube of hydrogen. Okay, 11,000 liters. Sorry, that means 1 kg of hydrogen you can store. So you might have seen the industrial cylinder, where there is the red color one, about 450 liter capacity at 150 bar. At 50 liter with at a volume of 50 liter and 150 bar, you can store only 420 grams of hydrogen. Okay, so you see here this the size of this reactor. This is you see the volume which is less than 6 to 7 liters. Okay, so with the 6 to 7 liters, and you can store hydrogen about 1 kg of hydrogen at near ambient pressure. That's more important, not at 150 bar pressure. Okay, so like this, these reactors are, we have also fabricated the reactor for hydrogen compression and cooling system for fuel cell application. And the bottom one, there is 3 sets, 3 reactors in one figure. These are the kind of prototypes, lab scale prototypes we fabricated for performing the parametric studies. Okay, go to next. Next. So basically this system, of course, you can see here the typical configuration. As I told you, this number of tubes and the even size of the tubes and orientation of the tubes, all these things need to be optimized based on the thermal models. We have nearly about 200 odd publication in this domain. For more details, one can go through it. And so you need to, of course, for any design, you need to approach a scientific, you have to do it in a scientific way. And they were not, of course, done in a random. So all these things are based on the thermal model, and these reactors are designed and then we fabricated. And you can see here the fabricated reactor. And once you fabricate, and you need to also identify the optimum operational parameters. For that, we have done the systematic parametric studies by varying the supply pressure, by varying the absorption temperature, by varying the desorption temperature, and also by varying the the heat transfer fluid flow rate. And we have done a lot of such studies, and maybe we can see some of the key results in the next slides. Go to next. Yeah, you can see here, for example, by varying the supply pressure from 10 bar to 30 bar. For example, when you generate hydrogen from the electrolysis process, if you go with alkaline-based electrolyzer, you can get the delivery pressure of hydrogen maybe about 20 bar. So which need to be stored. For example, if you go with this kind of system, if your supply pressure is 20 bar, you need roughly about 15 minutes to store the hydrogen, in a cylinder, in this kind of a vessel. And so for example, even if your temperature is about 25 degrees Celsius, you can get about 15 minutes. But if you have slightly lower temperature, you can speed up the reaction. Similarly, this is about this one small system we have taken where the capacity is about 270 or 280 grams. That means nearly about 1 big cylinder. Okay, that can be charged within about roughly about 900 seconds, means roughly about, you can say the how many? That is about 30 minutes. Okay, yeah, 14 next. 15 minutes. Yeah, 15 minutes. Okay, similarly, this is for the desorption. Here the desorption and the amount of hydrogen discharged. So the desorption rate, that is the delivery rate, should match with your end use application. Suppose you are connecting this device with the fuel cell, or you are connecting with this device with automobile. So whatever the demand, so the system should meet the requirement. So for that, what you have to do, you have to fine tune the operating temperature. For example, if you desorb, you supply the heat at 60 degrees Celsius, you can desorb it within about 3000 seconds. And still, if you want to slow down, for example, fuel cell application where we need the slow discharge of hydrogen. So where you can go, even if you have the temperature of about 40 degrees Celsius, you can extend the operation beyond 4500 seconds. Okay, this is depends on the requirement. You can fine tune the desorption rate. So this is very interesting system. And yeah, go to next. And so with the for example, for hydrogen purification, so if you generate, say, if you generate hydrogen, if you produce hydrogen other than electrolysis, for example, if you go with the biomass gasification, which is also again termed as a green hydrogen production, but along with the hydrogen, you will also have the impurities like CO2 will be there, methane will be there, nitrogen will be there, and little bit of CO will be there. Okay, again, how do you separate? That's a very challenging thing. So we have developed the metal hydride based purification system, which is successfully purify hydrogen. Even if you have the purity level of 20%, even with the 20% feed gas, you can get 99.999%. 99.999% of hydrogen you will get. So with this very simple technology which we will discuss, this technology stands for NTPC. And similarly, also we have also developed the reactor for the fuel cell application. For when you connect the system with the fuel cell, in addition to supplying hydrogen to the fuel cell, the system also deliver a cooling output in the range of about 5 to 7 kilowatt. That is the system what you are seeing here. Okay, go to next. So, so this is another reactor. For example, if you want to store 100 kg of hydrogen or maybe tons of hydrogen, whatever the system which we have seen earlier, that is the reactor with the embedded multiple cooling tubes. That may not be kind of a feasible option. The reason is that during testing, if it, out of 200 tubes, if one tube weld fails, the entire reactor will be wasted. Okay, it's going to be wasted. It's a really serious challenge. So here we made this kind of a tube bundle reactors. Here each tube will act as an individual reactor. So after the filling the alloy, during the testing, if any one of these reactor found leaking, so what you can do, you can isolate this reactor and the remaining system can be made operated. So with that, we have fabricated the system, and where we filled roughly about 26 to 30 kg of material. That means it can store about 600 to 700 grams of hydrogen, and we have tested for many applications. Okay, go to next. These are the design kind of innovation. Okay, yeah, next. Yeah, you can see here, this is the reactor which we have developed, and it's about 1 meter length. And so you can store nearly about 700 to 800 grams of hydrogen. Next. So this is the testing. We have also tested this reactor for many applications, for cooling, heating, and hydrogen purification, hydrogen compression, which we are going to see in the next few slides. Go to next. Okay, now you are seeing the bigger reactors. Anyway, just I wanted to give the glimpse so that you will also get some interest. And if you need further details, and either you can approach me or you can see our publication so that you will get the better design details. Go to next. Because certainly it's very difficult to explain all these things in the little 1.5 hour time. And so here also we have done the systematic investigation for the hydrogen absorption and hydrogen desorption by varying the supply pressure as well as by varying the temperature. And suppose here these reactors performs much better than the previous designs. Even if you have the supply pressure about 20 bar, within about you can say the 20 minutes you can complete the absorption process. Even with the 5 minutes you can get nearly about 70 to 80% of the hydrogen storage capacity. Okay, next. Yeah, so this is again another innovative design. For example, if you go with the magnesium-based hydride, the operating temperature will be above 300, 400 degrees Celsius. When the operating temperature goes above 300, 400 degrees Celsius, you cannot use liquid as a heat transfer fluid. Maybe you can use, but it will also produce the vapor pressure handling will be very difficult. Maybe you can go with the kind of a molten salt, which will highly corrosive. Okay, there are issues. So maybe you can go with air. But when you go, the air is the best one. But when you go with air, so your heat transfer characteristics of air will be very poor. That means the convective heat transfer coefficient is very low. So therefore, to increase the heat transfer characteristics, what we have done, we have made this three kind of a configuration 1, 2, and 3. In configuration 3, we have a kind of a disc in a fin, that is the brownish color is the fins, disc fins, which is welded in the on the inner tube, and at the center we supplied the heat transfer fluid, that means the air, and then it will come after reaching at the other end, then it will come again to the, it will flow through the periphery, then it will come out. So with this arrangement, of course, we got the much better design than you can see here in the comparison. So for example, for storing nearly about this 300 grams of hydrogen, our system took only about less than 5 minutes, whereas the system reported in the literature took nearly about more than 10 minutes. Okay, so here the performance is much better. Okay, go to next. So this is the reactor, and with this configuration, we made the modular reactor for storing about maybe about 25 to 30 kg of hydrogen. And now we are planning to develop a system which can store about 200 kg of hydrogen. This whole system will be integrated in a heavy truck, and so that the hydrogen in the filling station, the hydrogen will be charged into the the module, and once it is charged, then the truck will take it to the user point, and where it will deliver hydrogen at high pressure, maybe about 150 bar. So here we are planning to design hydrogen storage cum compression system. That means you can supply hydrogen at 20 bar, and the delivery it will deliver at about 150 bar. For delivering at 150 bar, you have to supply heat at maybe at about 120 degrees Celsius. Okay, that's the system you are going to develop. Next. Okay, so yeah, next. So again, this is the another system you have tested. You can go through it. The similar kind of things. Still, I have a lot of information. Quickly, yeah, next. Next one. Yeah, these are the results. You can see here the red one is our results. So this is much the performance of our reactors perform much better than the reactor reported in the literature. Okay, next. Yeah, this is again the another kind of a configuration like the longitudinal fin and disc metal fin and spiral fin and the tubular fin. Like this, we made a different kind of reactors, and very recently all these designs were tested. Among these, the reactor with the disc fins for the option 5 performed much better than the other 4 reactors. And based on that, we have done the fabrication also, and a few of the testing is already done, and still the testing is going on. Go to next. You can see the reactor. Next. These are the numerical studies, and again, these are the numerical prediction. Next. Yeah, now you can see the reactor. That's the reactor. The third one is the reactor with the configuration 3, that is with the filter. And so this reactor, of course, going to have the, this is the, so the configuration 2, that is the configuration 2, that is the annular, the reactor with, it's an annular fin reactor with 200, fins, annular fins. So that is the reactor, I mean, kind of a novel design, which we have done it, and now the reactor testing is going on, okay. For each reactor, say for example, in first two reactor we filled about 20 kg of material, and the second one we filled about 20 kg of material. But among these 3, the configuration 2, I mean, performed much better, okay, than the other 2 configuration. Next. Yeah, this is again the test results. For this disc filter one, you can see the results. Hydrogen stored maybe within about 20 minutes. This is with using the air as a heat transfer fluid. That's more important. If you use either water or maybe the fluid, you will get the much better performance. Okay. Yeah. Next one. This is the another reactors. Okay. Go to next. Yeah. So now, so the system can be also used for cooling application. For example, when you connect the system with the fuel cell, when you discharge hydrogen from the reactors, the endothermic, the reaction of the desorption provides you the cooling. Okay, go to next slide. You can see here the small, we demonstrated the cooling effect by using a small reactor. You can see here, when initially the whole reactor is at about 30 degrees Celsius, when you initiate the desorption process, within about 100 seconds, maybe about 10 seconds, the temperature drops from 30 to about minus 10 degrees Celsius. You can see here. Within about few seconds, you can see the formation of thick ice over the reactor. Okay. So this, shows or this, demonstrate the ability of the material for, generating the cooling. So therefore, the cooling, of course, the, generator during this process can be utilized for space cooling, or maybe the producing the chilled water, or many applications. In case of the pharmaceutical application, this is more beneficial, because here you are getting the cooling at free of cost. Okay. Next. So we also, by using these two sample reactors, identical reactors, we have built the system which can produce heating and cooling. This system, this is aimed at for the automobile air conditioning. Go to the, particularly for car air conditioning. Okay, go to next. So next one, you can see there are two small reactors, okay, which is coupled with the small hermetically sealed compressor. This compressor is designed for R134A refrigerant, not for hydrogen, but with some additional kind of features. With safety measures, we operated this compressor for hydrogen, and we got COP close to about 2.2 or 2.3. Okay, but now we are trying to design a compressor for hydrogen, dedicated hydrogen use. So maybe once we get the hydrogen which is dedicated for hydrogen, then we can get the COP close to about 0.4 or maybe about 4 or maybe 4.5. Okay, which is much competitive than your conventional air conditioning system operating with R134A or maybe the other refrigerants like R123YEF. Okay, go to next. So now what we got done with that small system, now we wanted to scale up to a higher level. You can see here the tube bundle reactors are used, and so this capacity is about 10 kilowatt, and again use the same compressor, and just to see whether this is feasible to use it, and we got very interesting results. Go to next. Yeah, you can see here in this one the temperature will be this nearly about, we operated about 500 seconds. You can say roughly about 480 seconds, and we could get near the temperature, we could get nearly close to about 12 degrees Celsius, and which is good enough for the car air conditioning. Okay, purpose. Go to next. And next is the purification. This is another interesting application. I told you, if you generate hydrogen from the biomass gasification, so you need a purification. The purification is very expensive, and even in case of the power plant industry, they use hydrogen as a coolant for cooling the generator. Okay, inside the generator winding, you can see the system is filled with hydrogen. Maybe typical generator capacity of about 600 megawatt capacity. You can see nearly about 130 to 150 meter cube of hydrogen filled inside. Okay, at a pressure of maybe around 10 to 15 bar pressure. So there the hydrogen purity need to be maintained above 96%. So if the hydrogen purity drops even 1% less, then the core loss will increase by about 0.5%. Okay, so imagine a system having a capacity of about 600 megawatt capacity. Even if the core loss increases about 0.5%, the amount of electricity wasted will be very huge. It's very significant. So what they do usually, so whenever the purity falls below 96%, the engineers flush the pure hydrogen. Okay, flush the pure hydrogen. Another side they'll purge it, so that the required purity will be maintained. So this is very challenging one. As a result, every the generator spend about 15 to 20 cylinders. Okay, mainly to maintain the purity. So in order to minimize this kind of mitigate this challenge, or maybe find the solution for this challenge, we proposed this technology. So our technology, basically, when you supply hydrogen to the metal hydride absorb only pure hydrogen. The remaining impurities will in the void space. Now look at this in this slide. The green is the hydrogen and black color are the impurities. So during absorption, you can supply hydrogen along with the impurities. Then go to next slide. Once the material absorbs the hydrogen, all the green dots that will go into the metal lattice. Okay. Then after this, only the impurities like the black dots will sit in the white space. Once the absorption is over, now what you can do, you can open the so-called the impurity purge valve. Okay, go to next. So during the purging, you have to supply cold water maybe at about 20 to 25 degrees Celsius. After that, once you open it, all the impurities will go. Then after purging, what remains inside the system is 100% pure hydrogen. Okay. Now what you can do, maybe you can supply the heat maybe at about 40 degrees Celsius or 50 degrees Celsius. It depends on the configuration. Then you dissolve the hydrogen from the system. So during dissorption, you will get high pure hydrogen. Okay. That means during the supply, even if you supply hydrogen at 20% purity, then during the dissorption, you will get 99.99% purity. Okay. So which cannot be achieved in any of the purification process. Go to next. So this is the system was built and the technology is transferred to NTPC for the commercialization. Okay. This is the complete layout of the system. Go to next. So I'm going to show you some of the illustrative results. For example, we have taken 10% CO2 along with 90% hydrogen. This is the gas chromatography. And flushing out sample, all CO2 will come out. Then if you dissolve the hydrogen by heating it at maybe about 50 to 45 degrees Celsius, the dissolvent sample contains 99.99% purity, and you have only 0.01% of CO2, which is almost negligible. Okay. So this is the photograph, shows the demonstration of our system, connecting at the, the main, NTPC power plant, where they're given 96% purity, then we delivered 100% hydrogen. Okay. This is just to demonstrate the technology. Go to next. Yeah. So, we developed the three-stage system, a three-stage purification system. Suppose if the purity is less than say 20%, and you cannot use single stage may deliver 90% hydrogen. So to get 99.9% hydrogen purity, then we build this three-stage system. All the three materials are connected in series. Go to next. Yeah, you can see here there are three systems here: the La CCM nickel and LaNa5 La nickel aluminum. There are three systems. Suppose if the if the purity is above 90%, you can operate the first system. The purity is around 70%, then you can operate the first two systems. If the purity is maybe close to 25% or 20%, then you can operate all three systems. Okay, with this all three systems, you can deliver the high pure hydrogen. Maybe I will show you some of the key results. Go to next. Next, yeah, this is the photography of the complete system. Okay, keep going. Yeah, again, you can see all the compact system of hydrogen purification. There are three reactors you can see here. Next. Yeah. So, for instance, here you have 30% methane. We have prepared a sample with the 30% methane and 70% hydrogen. With the single stage, we got 96.6%. Okay. Go to next. Yeah, this is with the 20% hydrogen. With the 20% hydrogen, we got about almost 100% hydrogen. Okay, with the 20% nitrogen impurity. Go to next. So yeah, so here just to illustrate, even for example, nitrogen percentage varied from 10% up to about 50%. There is 50% nitrogen and 50% hydrogen. Even if you have 50% nitrogen, with the single stage, you can deliver about 97.9. That means 98% pure hydrogen. Okay, that is which is very high. Sorry, 97%, which is very high. Okay, and even with the methane, also with the single stage, you can get about 96% hydrogen. Okay, if your impurity is about 50%. So like this, we prepared the gas sample by mixing nitrogen and methane and CO2 and CO and all the 4-5 gases, and we have done the extensive experiments, and the major findings are, of course, the patented. We got the patent granted also. For the next. So maybe you can skip it. I think too much for you to digest. Go to next. Yeah, we can go to next. I think this may not be. This is actually, it's a hydrogen kind of transformer. If you have the heat input of about 300 degrees Celsius using our system, you can upgrade the heat input from 300 to about 350 degrees Celsius. At the same time, you can also generate cooling at about 0 to 20 degrees Celsius. This is called the poly generation system. This system also we have built and tested. Okay, now we are planning to build the industrial scale system. Okay, go to next. Yeah, you can go to next. These are the system which you are seeing now. Yeah, it's already, yeah. So another technology is the hydrogen compressor. This already told you. So the electrolyzer, you are producing hydrogen at about 20, maybe about 20 per max. Okay. So if you want to store it in a type 2 cylinder, you have to pressurize about, you can say roughly about 150 bar. If you want to store it in type 3 or type 4 cylinder, then you need to pressurize hydrogen up to about 600 bar. So usually the compressing hydrogen is not a easy task. It's a tedious process. It's an energy consuming process. You have to spend nearly about 35% of the energy only for hydrogen compression. Again, these compressors are very, very expensive, and maintenance of these compressors are very, very, kind of difficult. So therefore, by using our technology, just by utilizing the heat input in the range of about 20 to 150 degrees Celsius, you can pressurize the hydrogen from about 2 bar pressure up to about 450 bar pressure. Okay, so we have demonstrated this technology, and also we have built the industrial scale system, and then the technology is transferred to NTPC, which we are going to see some of the key findings next. Okay, so this is the 3-stage system. The first stage can compress hydrogen from 2 bar to about 40 bar, and the second stage from 40 bar to about 80 bar, and third stage from 80 bar to 450 bar. But all 3 stages are operating between 20 degrees Celsius to about 120 degrees Celsius. Okay, this is the system which we have built. This is the schematic view. Go to next, and keep going. There will be some animation, I guess. Keep going, keep press. Next. Yeah, you can see here the photographic view of the system. This is a big, really industrial scale. Okay, and the whole system is transferred to NTPC for the commercialization. Next. Yeah, next one, you can go through it. Maybe I'll show you. See here. In the third stage, even with the 145 degrees Celsius input, we achieved about 160 bar pressure. Because beyond 160 bar, we didn't go because we don't have the type 3 or type 4 cylinder to store the hydrogen. But however, with the closed loop, when we heated the system up to about 85 degrees Celsius, we achieved 300 bar. Then when you heated the system up to about 120 degrees Celsius, we got about 450 bar pressure. That is beyond our, you can say the, our target. Okay. Next. So what is the way forward in the, as per the, the automobile is concerned? It's our one. And so every country has their own hydrogen, roadmap. Maybe if you Google it, the country status report on hydrogen and fuel cell, and you can get the report, our report, myself and Professor Pratibha Sharma and Professor Rajalakshmi, Dr. Rajalakshmi, we prepared a report, and which was published almost 7 or 8 years back. You can go through it, where we have given some complete comprehensive view. But however, now our vision is changing, and now recently government has announced the hydrogen valley, and we are planning to transform our present hydrocarbon based economy to renewable energy based economy by 2047, and to achieve the hydrogen, the carbon neutral by about 2070. But however, our government is planning to achieve the carbon neutral by about 2047 itself. So when you go such a huge, when you have such a huge kind of target, without hydrogen you cannot implement. Okay, so basically hydrogen, it's a kind of provides the solution of large scale electricity storage, which is generated from the renewables. So when you want to store, huge amount of electricity in the tune of gigawatt, okay, the only possible is you can store such a huge amount of electricity through hydrogen, okay, not in the other form, okay. So by 2030, we are planning to produce about 5 million metric ton of hydrogen through the green, and by this is going to increase by about 10 million metric ton by 2035. That is our target, and where the produced hydrogen will be extensively used in automobile and steel industry, ceramic industry, and petroleum industry, and so on. Okay, So as of now, we are in the first generation biofuel, and soon we are going to second generation biofuel. That means the current 10%, this ethanol will be increased to about 20% ethanol and 80% petrol. That soon we are going to have it. And now the electric vehicle is getting penetrated into the market. And so once we have the required infrastructure, and the electrical vehicle will boom. And the problem with the electrical vehicle is the temperature. Okay, the thermal management is the very key issue. Usually, if you operate the electric vehicle between 25 to about 40 degrees, more effectively between 30 to 40 degrees Celsius, it works better. I mean, the battery performance will be much better. Suppose if the temperature goes above, say around, maybe goes close to about 55 or 60, then what happened? The electrolytes start decomposing. Okay, when the temperature goes above 65, then it will catch fire. That's the reason you might have observed, might have seen in the newspaper in many places the two-wheeler and everything getting started fire. So again, the electric vehicle also, again, the lithium is the key kind of issue, and we don't have only across the globe, only one country is having large resource of lithium. So if you rely on lithium-based, the battery technology, we will be in trouble. Again, the mass scaling will be difficult. And another challenge is the recycling of all the batteries, another key challenge. So therefore, these are only the intermediate solution. By 2035, our government is planning to go in a big way in hydrogen. So once we, of course, invest heavily on renewables, the only possible solution is you have to go hydrogen. Okay, without hydrogen, of course, you cannot sustain the technology. Okay, go to next. Next, please. So this is one of the very famous project which was successfully implemented in Germany. Okay. So so here, so they have excess electricity of generation of about 30%. So 30% they are generating electricity in excess, mainly from the renewables, that is solar, PV, and wind. They have huge wind park. So whenever they generate excess electricity, what they do, they convert it into hydrogen. So earlier, what they do, whenever they produce excess electricity, the excess electricity will be transferred to Poland for their use. For transferring the excess electricity to Poland, German used to pay for it. Otherwise, their grid will fail. Okay, this is the this it's a kind of economic kind of a crunch for them because they are selling the electricity. Further, Germany is paying for it. So then they thought about it. Then they proposed this solution. This solution works very well. So whenever they have excess electricity generated, and then it will be converted into hydrogen through the electrolysis process. The hydrogen will be stored in the form of metal hydride, or some part of hydrogen will be dispensed to the automobile through the gas dispensing station, and or some part of hydrogen will be injected to the national gas grid along with biogas or the CNG, which will be used for cooking and other industrial application. Okay. So in that way, or later the hydrogen can be also used for producing power through the electrolyzer. So everything is kind of things. For example, even in India near Kanyakumari, many of you might have seen the huge windmill park. They have the capacity of roughly about 400 megawatts or something. So during the peak wind season, only 75% of those windmill used to operate. Remaining 25% usually they disconnect. The reason is that when all 100% this windmill operates, the grid will not sustain because the power generation will go beyond its design capacity. So in order to safeguard the grid, so they disconnect almost 25% of the windmill. Okay, actually basically we are not utilizing it. We are underutilizing the resource. So what is the solution? The solution is, okay, whenever you have excess power generation, either from the wind or either from the the hydro, you convert the excess electricity into hydrogen. Okay, so here the generation of hydrogen is almost at free of cost. Anyway, you have the excess electricity which you are not consuming, it will go waste. Okay, so technically you can generate hydrogen at free of cost, and this hydrogen can be used for later. You can use it instantaneously, or you can also use it later. Okay, so in that way you can utilize 100% renewable energy, and you can also have a cost-effective solution for storing electricity which is generated from the renewables. So this is the sustainable solution. So India also going to adopt such kind of solution very soon, and we are also going to implement such kind of project. Okay, go to next. Yeah. So many of you think that hydrogen is a dangerous fuel. It may be flammable and it is a and highly explosive. You might have seen many such versions, but it's not true. And there are two kind of these experiments. Whatever you are seeing, the fire. This experiment was performed almost 15 years back, and the similar kind of vehicle was taken. One is the petrol vehicle where you have seen the bulk fire, and there is a hydrogen vehicle. So in both the vehicle, the similar kind of damage has been made. Okay, and so when the accident happened in case of the petrol vehicle, it got into the explosion where the whole car is damaged. Whereas in case of the hydrogen fueled car, if there is a leakage, what happened? If there is a fire, the flame try to move in the upward direction. The reason is that because of the lightness, because of the hydrogen is very light gas when compared to air. It is how much time? It is roughly about 15 times lighter than the air. And since the diffusivity and the flame speed is very high, and the flame try to move in the upward direction. Okay, so as a result, there nothing will damage, and you will be safe. Okay, the another issue is that embrittlement is the key issue, but there are solutions to tackle the embrittlement. Okay, so therefore hydrogen is really absolutely safe, which is almost safer than the petrol and diesel. Okay, go to next. Okay, so this is about the status, and the mostly you can see if you produce hydrogen from the biomass, roughly about 150 to 170 rupees per kg. But again, another 150 rupees you have to add for purification. Natural gas also 140 to 160 rupees, maybe another 100 rupees you got to spend for purification. Solar PV at present, so for generating 1 kg of hydrogen from the electrolysis, roughly you need to spend about 55 units of electricity. So if you spend 1 unit maybe by 3 rupees, then with about 150 rupees you can generate hydrogen now. Okay, and here there is no question, there is no need for spending money for purification, because through the electrolysis you will get high pure hydrogen. Okay, and so there are many things are coming up. For example, now the Australia is the world leader for hydrogen production. They are exporting hydrogen to Japan, and at a rate of about $2.5 to $2.7. By 2030, they are planning to reduce the hydrogen production cost by about $1.9. That is their target. Across the globe, there are so many hydrogen fuel. The filling center it has come. For example, in Germany, they have nearly about 500 refilling this one. For Korea, they are going to set up about 700 refilling station by 2030. India also, we are going to have about 100 such number of refilling station futures, and many such efforts being made. And for instance, again, they go across the globe, and many countries discouraging the production of diesel engine. The issue is that because of the pollution. And similarly, India is also having the kind of a similar plan. And by 2030, India is going to promote the electric vehicle, and in addition to parallelly with the hydrogen vehicle. The hydrogen vehicle will be promoted in two ways. One is the fuel cell based vehicle, another one is the direct IC engine based vehicle. This both the technology going to come. Okay, so now very recently India has go to next. Government has initiated the next one. The 3 mission mode. Go to previous one. 3 mission mode they launched it. One is the previous. Yeah, next. Yeah, next. No, next. One more. Yeah, you keep it. So there are 3 missions. One is the renewable energy mission. I told you, like we are planning to achieve about 50% renewables by 2030. Already we reached it. Now we are 43%. Only 7% only need to add. And electric mobility, again, that is also in pipeline. And a national hydrogen mission by 2000. It's already government has cabinet has approved about 22,000 crore in 2023, and many more such things are coming up. So under this mission, the objectives are like they are going to, as per this one, India is going to be one of the green hydrogen exporter of hydrogen to the world, and they are going to create all the infrastructure, for hydrogen one, and also reduce and use hydrogen as a feedstock for the many industrial application. Again, if you use hydrogen as a kind of a fuel in the automotive sectors, and support many R&D project and all these things. Many such things have been done. And the Department of Science and Technology, now the Anusandhan Research Foundation, AINR, is taking care of all the activities. And very recently, the famous, program called Hydrogen Valley has been, announced, sanctioned, and government is going to this fund 3 such valleys or 4 such valley. One is in Kerala, another is in Hyderabad, and in Gujarat, and then in Bhubaneswar. They are going to fund this 4 valley, and where all the hydrogen related activities will be taken up. And so India, the IIT Tirupati also going to be one of the center of excellence on hydrogen energy very soon. And we already submitted a very big proposal, and the proposal is under evaluation. Hopefully we'll get it. Go to next. So under this value, you can see here, the main target is to produce hydrogen at about $2, which includes the hydrogen purification, hydrogen production by 2030, and produce about 5 million metric ton of hydrogen, green hydrogen by 2030, and ramp up to about 10 million metric tons by 2035. This is our things, and make India as one of the green hydrogen exporter, and then expand the use of hydrogen for many industrial applications. These are our mission. And go to next. Yeah, okay. So the hydrogen valley, basically it's a geological, hydrogen valley is nothing but it's a kind of a location, particular location where the the hydrogen, major hydrogen technology, including hydrogen production, storage, and transportation and utilization, will be of course explored. And then the industrial scale prototype will be developed, and this valley is going to be kind of a nodal center for providing adequate training and testing and all these things. And so the industry and academic institute can go to the hydrogen valley, and then they can get trained. Okay. And so the valley, in the hydrogen valley, the many things will be taken up. For example, the end user application, the clean heat and power industry application, which includes the steel and ceramic, and this steel, ceramic, and as well as the the cement industry, and transport, both the 2-wheeler and 4-wheeler and marine and aviation. All these things will be included. And even in the heating also, the domestic cooking also going to be explored very soon. Okay. So now I will give you a break of about 5 minutes now, 5 to 10 minutes. So this is about the hydrogen energy. Maybe I will open this talk for discussion. If you have any doubt or query or whatever, maybe you can discuss. So maybe I will give you a 5 minutes break for your breathing. There may be few time, maybe another 10-15 minutes. I wanted to highlight one more technology. This is also comes under the Sustainable Development Goal number 7. Yeah. So Professor Saravanan, you can ask the if anybody is having doubt or anything, they can directly they can ask. They can unmute their mic. They can ask.
Yes, Professor. Yes, Professor. Thank you very much for your lucid presentation. I will say the vote of thanks at last. Dear participants, if you have any clarification, queries, please post to the
directly they can ask. You can provide the kind of the option for them to ask.
Yes, sir. Yes, sir.
You can enable them so that directly they can talk to me. Or maybe if you have any issue in talking, maybe you can, you can type in the, chat box so that I will read, and then I can, of course, I can, reply. There are so many messages are coming. Yeah. So yeah, please, if you have any questions, you can post in the chat box also.
Participant, please open your mic and raise your queries.
Good evening, sir. This is Kamal Sangran.
Yeah, please go ahead.
Sir, I would like to tell one thing, sir. Excellent presentation. Particularly, I have very much enjoyed this session. One more thing. Till now only I came to know the cost of hydrogen storage, particularly the 3 forms, so as to, that is gaseous state and liquid state, particularly -253 degrees Celsius, and solid state. Such a great data, such a wonderful data. The people, those who are doing their research work in the cryogenics area or in liquid hydrogen area, excellent, sir. My personal congratulations to you, sir. Excellent presentation, sir. Thank you very much on behalf of our mechanical staff members and all other faculties, those who are joined. Thank you, Professor.
Okay, thank you. You have any query? You have any question?
No, sir. No, sir. Thank you, sir.
Okay, anyway, thanks for your appreciation. Yeah. So any queries, please, you can feel free to discuss. This is like a, you don't need to get kind of, afraid, don't feel any shy. This is, I wanted, kind of interaction with you guys.
Hello, sir.
Yeah, please go ahead.
Tell me, Mr. Vinod Kumar, what is your query?
Hello, good no person. Hotel we used to.
Yeah, Mr. Vinod Kumar, you can type. You have difficulty in speaking.
George. No, my purse માં પૈસા નથી. Riyam Chalam.
Nirav Maniar, what is your query?
2800 રૂપિયાનું ચાર્જ છે. એમને ઘઉં તને કહું છું. બીજી વાર જાઉં 1600.
So maybe, so okay, anyway, thank you. Anyway, definitely we will share the presentation and the course coordinator already they have taken my presentation and they will of course share it to you. Okay. So anyway, thank you for your patience. So maybe I can take maybe another. Okay, sorry. Yeah, Saravanan. Yeah, my mic was, muted. Saravanan, you are there? Professor Saravanan. Hello, Saravanan. Please, course coordinator, you are there? Anybody is there from the course coordinator side?
Sir, I am here, sir. Tell me, sir. Tell me,
Yeah,
sir.
yeah. So how much time I have?
No, sir, if any queries, we will clarify it, sir. Otherwise, we will close down the session, sir.
No, maybe I need to take another 10-15 minutes. I wanted to give some, maybe one area. I will talk maybe another 5 minutes. Then maybe we'll discuss about the career option, which usually I'll do it for the PhD and the young, researchers. So go to the next slide.
Next slide.
Yeah. So next thing is one of our innovative technology. That is this particular technology received the Abdul Kalam Technology Innovation National Award, which is higher than any of the Padma Awards. This I got it during 2021. This is the development of energy efficient, the eco-friendly porous radiant burner for cooking and industrial application. So this technology provides about 30 to 60% fuel saving and also reduces the emission about 95%. Okay, that is a important thing. Go to next. Anyway, I won't take much time. So basically, just keep enter one more time enter. So in the conventional burner, you can see the burner what you have in your home and then your hostels and your college. Basically these are the pre-flame combustion, and so you can see the flame, when it burns, and above the burner head you can see the flame. So this is called pre-flame combustion. Can you just enter it one more time? 2 times enter. There is an animation. Yeah. So we developed a burner, it's using the ceramics, and our burner consists of 2 layers of porous matrix. And you can see here there is a dark, red color that is, made up of silicon carbide, which is acting as a combustion zone. Below the one that is the white vertical line, that is called a preheating zone, which is made up of alumina. Okay, both are low cost ceramics. And when you supply the fuel, fuel through the mixing through the nozzle, it gets mixed. And when it reaches the so-called the reddish, dark red color combustion zone, you can combust at the top of the burner. And since the combustion is happening inside the highly conducting and radiating porous matrix, because of the radiative heat transfer, some part of heat will be transferred back for preheating the incoming air fuel mixture. As a result, the air fuel mixture is preheated from atmospheric temperature to about 150 degrees Celsius. This preheating helps us in achieving 100% combustion. Since the combustion is happening inside the highly conducting and radiating porous matrix, and because of the increase in residence time, and this also increase the combustion efficiency. Another interesting thing is, since the combustion is happening inside the porous matrix, and the flame will be submerged inside the the matrix, and you don't see the flame. And from the surface, radiation travels at a speed of light. Whereas in case of the free flame combustion, the mode of heat transfer from the flame to the previous one, the flame to the vessel is convection. Since the gases are having low conductivity and low emissivity, the rate of heat transfer from the flame to the vessel is very low. As a result, the heat loss will be very high. That's the reason the thermal efficiency of the conventional burner, usually in a practical scenario, it will be lesser than 60%. So utilizing this technology, I think you can unmute the mic to everyone. Okay, so utilizing this technology, we developed such burner, for example, for the commercial scale the kitchen, and you can see here for the power output of about 5 to 7 kilowatts. So we achieved about 40% fuel saving with the commercial burner. This burner can be used effectively in your college hostel. Here we got about 35% fuel saving for the bigger burner. Even for the cluster burner like the 3 burner, this can be also used for mass scale cooking application. Here got about 35 to around 30 to 35%. With the biogas also, we developed such technology. We achieved about 25% fuel saving. So all these savings are done with respect to actual cooking at the protocol given in the BA standard. And besides that, we got about 95% reduction in CO and NOx emission. Go to next. So next one. Yeah, you can see here with the domestic also we developed the burner now, and here we got about 82% fuel the thermal efficiency. In terms of fuel saving, we got about again 40% fuel saving. And you can also see here in our burner the CO emission is almost lower. You can see here the maximum about less than 50 ppm, whereas the conventional burner can go up to about 600 ppm. You can see compare. The NOx from our burner is almost zero, because in our burner we minimize the surface temperature well below 1050 degrees Celsius. This won't allow the formation of thermal NOx. Go to next. And next one. So we have also done the so-called the life cycle assessment of all our technology. There are about, see, when you commercialize any product, so the new product, the impact created by the new product on the environment should be much lesser than the existing product. Then only your product will be economically and as well as the environmentally sustainable. Rather than sustainable in terms of economically, but it should be also sustainable environmentally. There are about 16 environmental mitigation category. So the impact created by our burner on these 16 environmental mitigation categories are almost like 6 to 10 times lesser than the conventional burner. Okay, so therefore our burner is not only environmentally sustainable, and also it is also economically viable by providing about 30 to 60% fuel saving. Okay, so the payback period of our product is less than 2 months. Some of the product, and some of the product maybe takes about maybe about 4 to 5 months. I think you must be heard about it. Any product having the payback period of less than 2 years, which is kind of, people say it's a successful product. But our product is giving the payback period is less than 2 months. Okay, go to next.
Next slide.
Next slide.
Yes, sir.
So this our technologies, of course, we distributed this burner to various IIT Madras and Anna University also we given. And now we are going to distribute this house to various IITs. And here we have one famous temple, Sri Kalahasti temple. The entire temple is equipped with our burner. This is kind of a pilot project we have taken, and we installed about 36 such burner. And this for last 1 year, these burners are operating without any the safety issue, and provides about 35 to 40% fuel saving in actual environment. And the are very happy, and you can see some of the photograph, real-time photographs taken here. Go to next.
Next slide.
Hello, sir. Could you hear me?
Yeah. Here maybe can you click on this burner? There is
some problem in the mobile. Wait, I'll leave and get back.
Sorry.
It was going to the driving mode.
Can you first one click it? The first figure. Click on it. You have just to keep the cursor there. Hello. The first figure.
Yes, sir.
Yeah. The first figure, keep the cursor. Mouse. And this is a video. It can play.
First figure.
Yeah, just click it. Yeah. Click it. Yeah. You can see. Yeah, it's fine now. Yeah, they are seeing. You can see here. This is the video. You can see this burner in operation. You don't see any flame. Okay.
Yes, sir. No flame at all.
Then second one also. Second one, just click it. Yeah, click that one. Yeah, you can see here. It's a completely flameless combustion. Okay. Yeah. And
second also no flame, sir.
Yeah. This also. See, sometimes the cooks also wanted the third one is the biogas with biogas. Okay. Okay. That's
third
also our with work LPG, PNG, CNG, biogas. Any gas is fuel, and also we also developed the technology for liquid as well. Go to next.
Next slide.
Yeah, this first one you can play it. Yeah, you can see here. So it also provides the almost 3 to 4 years increase in life to the cooks, because this completely reduces the CO emission and all these issues. And so the people who are using this one, they won't have any respiratory related issues. So in addition to providing all the benefits, it also provides the better working environment. So these are the go to next. So this is some of the go to next one. Yeah. See, there the cook actually wanted some kind of a flame also, that also we made it, because just for your psychological things, they wanted some flame, half flame and half kind of the submerged mode, that also we made it. Okay. So it is possible in anything working in any mode. Go to next. So you can see here, this is just for go to next. This is real-time data. For instance, for example, this for making the the fuel. You can see, look at this amount of fuel consumed. Okay, they have taken. This is our burner. The first two are the our burner for preparing about. This is about 50 kg of rice, 30 kg jaggery, 50 kg. This is for preparing maybe about this I think about 200 kg of sweet pongal. Our burner consumed about roughly about 5 kg of LPG, whereas their burner consumed about 6.78 kg of LPG. Okay, so this is the direct one, and almost everything is same. Okay, so this is for preparing a huge amount of pongal. This is continuously they are preparing in the in the temple, and like this they prepare 1000 kg pongal also. This is just one example. For all the cases, it gives about 30 to 35% savings, and for the small capacity, we got up to 60% savings. Okay. Okay. So this also, of course, the certified by the the BIA, the LERC, that is the only central government testing agency which is located in Bangalore, and they estimated as per their one protocol, and our burner is about 62.5% thermal efficiency against the standard efficiency of about 45%. Okay. Yeah. Go to next. These are some installation done at IIT Madras. Okay. So we have about 9 granted patents. Okay, on this technology. And just for give your idea so that people have some kind of a motivation in developing such kind of a product in future. Go to next. Next one. Yeah. So yeah, this technology, of course, received several awards and all these things. Now coming to the this core, because there could be few PhD students, and then some may be interested in taking up their career in higher studies. So these are some of the areas where now the government is investing, and we will be having the huge demand. For example, the energy sector, we have the demand in hydrogen, battery and EV, and hybrid engine also going to come, autonomous vehicle, drone. The smart material is another area where our government is planning to spend huge money on the semiconductor and biomaterials. There will be one. And civil engineering, we have the huge demand, particularly 3D printing, fire safety, weather monitoring, construction management. And coming to the electronics and communication, the green communication, 5G communication, power transition through the microwaves, and in the physics, high energy physics, quantum computing. There are huge, options in the core engineering. And so I request, of course, people to, give due consideration, due importance to the core engineering, because as long as the core engineering exists, then only you will have the business, then only your IT, all the data analytics, artificial intelligence, all these stuffs can flourish. If you don't have core engineering and nothing, of course, we cannot sustain. Okay, the core is the which is the basically backbone of any business. Okay, so and there is also a huge opportunity for higher studies in India, particularly in core engineering. And the next 5 years, we need about 10,000 PhDs, to cater the various needs. And we don't have, for example, if we take mechanical engineering, we don't have good PhD in industrial engineering. And industrial engineering is the area where we don't have PhD at all. And even in the for example, the industrial engineering, even for example, even the HSS for the psychology, we don't have people. In statistics, we don't have people. And the electronics, the control, the system, we don't have good PhDs. I have been in the part of recruitment, faculty recruitment for many IITs and central and state universities in ISRO, DRDO, and really we are starving faculties in these areas. And so even the EV also, we need faculties. Hydrogen energy, there is a huge demand. So please try to concentrate here. And maybe if you are a faculty, please identify good students in your in your department, and ask them to maybe you motivate them to write GATE. Once they qualify the GATE, they can come for PhD even if they have BTech degree. If they have BTech with about 85% marks, they are eligible for direct PhD. And even in institution, IITs also, we have the fellowship called Prime Minister Research Fellowship, PMR fellowship. If they qualify in this fellowship, in the first 2 years, they'll get about 80,000 rupees per month as a fellowship. And then third year and fourth year, they will get 1 lakh rupees. This is a non-taxable income, okay, every month. It's a fellowship. And in addition to that, they will be also paid 2 lakh rupees every year, mainly for, the, travel. They can visit any country, they can visit other labs in India or abroad. Its opportunities are huge. And, in addition to that, the government also support travel grant and many other fellowship. Okay, so particularly they get a PhD from IITs, and of course they will find the better career option in the near future. Okay, go to next. So that's what I wanted to say. In IITs, they can enter in a PA. If they have BTech level, they can do MTech or MS or PhD. MTech, they can do PhD. In case of BTech, they need to have valid GATE score to join either PhD or MS. In case of MTech, they don't need GATE score. They can join directly. They can join PhD. If they have MS qualification, they can join MS or PhD. So the opportunities are huge. Okay, and so the government is also giving a lot of fellowship. For example, in a Fulbright fellowship and base fellowship, Indo-Canadian fellowship, Commonwealth fellowship, and then Asian Shark fellowship. There are, you can more than 10-15 such fellowships are available. So all the faculties, please visit the DST website, CERB website, and you can see the the opportunities, and you can try to avail. So particularly for the research, in the academic, the contact is very, very important. Okay, you need to have a professional contact. Okay, if you want to groom yourself, if you want to grow yourself, you need to have contact, because the contact helps you in publishing a good paper and getting a project and getting a better students and getting postdoctoral opportunities. All these things, the contacts are very important. Okay, yeah, next. Okay, so this already I have mentioned. So so what I want to say here is that if you maybe if you take the core engineering as your career option, if you serve about 15 years, and you will reach the much higher position where the IT sector cannot reach. Okay, the IT sector initially they will have a better growth. Maybe after 5 years they will reach the saturation. Maybe after 10 years they won't get any increment at all. They won't get any kind of the appraisal will be almost zero. Whereas in core industry you will have a steady growth. After 10 years, if you see your position, you will be much higher position than your IT sector, colleagues. Okay, so that always you keep in mind. Okay. Yeah, next one. Okay. So yeah, that's all from my side. Okay, so just I wanted to add up this few information. So whenever I deliver a talk, and always I give a kind of some motivation for the young researcher to come to higher studies, because now right now in India we lack most of the IITs. In fact, I have nearly about 10 openings. I have nearly about 12 projects. In all projects, I have openings. If you know any of your student or your colleague, or maybe your friend, or who, or maybe who is having kind of interest in pursuing studies in IITs, they are always welcome. You can do write to me. And the only thing is they should be bright, and they should have good academic background. And if they have GATE score, that is well and good. And even if they don't have GATE score with the MTech qualification, and if they have good vision and determination, of course they can approach me. Then definitely I will provide them the opportunity. Okay. So yeah, so thank you very much for your patient hearing again. So the floor is open for discussion. If you have any questions, you can feel free to ask. Thank you. Yeah, you can unshare the screen now, so that I can see their face. Yeah. Yes, please.
Participants, any queries?
I think people are tired, or there some are feeling sleepy. Maybe some may be having dinner. So that's the problem. There are advantages, there are disadvantages in
online.
We cannot see what this one. Yeah, if you have any queries or any if you want to have any interaction, of course you can feel free to discuss. Okay, so one has asked what are the key technological challenges
facing the development of hydrogen fuel cells for automotive applications.
Okay, so again the materials only the posing the one the technologies, of course simple, and it's a thing, but only thing is the cost of the fuel cell stack, that is bit high. But in India, no one is making the stack in India. Okay, even the stack, mainly the stack and the bipolar plates, these two are the major key components. And so currently, of course, we are getting it from outside and trying to assemble here. And in India, we are only fabricating we are assembling it. Okay, so now the effort being taken by few research institutes, for example, some of the IITs and CSRI lab, and even ARCI, they started fabricating these stacks in India. Even the metallic bipolar plates being also made. And once you scale up the technology to the kind of a kilowatt level, like the 5 kilowatt and 10 kilowatt, and if we make them here, and so I think we can overcome all this technological barrier. And again, there is also the the demand and supply equation. So when when the cell phone was introduced during 95 or 96, the cost of the cell phone during that period, it was close to about how much? It was 25,000 or 30,000 rupees something. The size of the cell phone was like bigger than the brick. Okay, and when you made a call during that time, you have to pay 25 rupees for outgoing call and 20 rupees for incoming call. Okay, that was
exactly,
but now what is the current scenario? It has the cell phone size. You can get the cell phone as slim as just like a like a paper thickness also, it's coming up now. Very slim cell phone.
Very thin.
Even the cost of the call is almost negligible. It's all about the demand. Okay.
Yes,
When
sir.
there is a demand, and always, many people started working on it, then there will be many technology revolution will come, then the cost will go down. Okay. So I'm sure now this the fuel cell is many startups in India started working on this fuel cell in across the globe. Also, many companies have started exploring, and obviously, and then when the fuel cell market expand, then the cost will come down. All the technology barrier will go, and then the the things will be sustainable. By 2030, you can see the cost effective fuel cells will be developed in India and also marketed in India. Okay. So as such, there is no kind of a challenge, but again, time only the solution. It will evolve with time. Okay. So any other question? Okay. Professor Saravanan?
Yes, Professor.
So excess generator by renewable energy sources, we can store hydrogen tank and utilize the for servicing. Yes, you can see for in case of metal hydride, you don't need to supply the heat. Suppose if you design a metal hydride which can dissolve hydrogen at about 2 to 5 bar pressure in the temperature range of about the 10 to 15 degrees Celsius, you will get cooling during the desorption. You don't need any heat. Okay. But for example, if you are choosing a hydride which can dissolve hydrogen maybe around 10 bar pressure, you need a 10 bar pressure maybe at about 50 degrees Celsius, you can use the solar heat. Okay. So that is flexible you have. Yeah. Okay. Okay, then so Saravanan, maybe probably it's already 10 o'clock now. Okay.
Yes, sir.
So you can
shall we move on to the Thanksgiving session, sir, for a minute?
Yeah, fine. Anyway, it's yeah, okay, you can go ahead. Yeah.
Yes, sir. Dear Professor Dr. Muthu Kumar, sir, it is a very informative and lucid and practical experience presentation by you, almost 2 hours, right from 8 p.m. to 10 p.m. As a coordinator, I am looking into 4 pillars of our Indian Constitution. First, number 1, you have given about hydrogen energy storage and its application. Second, another very interesting and informative one, the fuel burner optimization, and it is a low-cost one. And as you told, it is more than a Padma Shri award. That kind of thing, very interesting and informative one. Third, you have given the career opportunities for all the participants and those who are involved in the research level. Last but not the least, you are also encouraging the young students, those who are doing BTech, MTech, and trying to find out the problems of PhD. You have so many projects with the inclination towards you. You are ready to help them. So that kind of broad mind, Professor, you have. So on behalf of AICT, ATAL, FDP, on behalf of my own institute and my own official and personal, we express our sincere thanks to our core of the heart with our co-coordinator, Dr. Vijayan, and all the behalf of all the participants. 2 hours long presentation without any tired and highly informative one. We thank you very much, sir.
Okay, thank you, and thank you, Professor Saravanan, and thank all the participants for listening. And if you need any information, any of the materials, you can don't, you feel free to write to me. Of course, if I am busy, definitely my scholar will respond to you. Thank you, and all the best for your career. And also
thank
all the best.
Thank you so much, sir.
Professor Saravanan, thank you for taking such a great initiative, because you, of course, you brought, nearly about 150
thank you, sir.
researchers, across the, India into a single platform. And thank for taking this initiative, and all the best for the course. Thank you.
Thank you very much, Professor.
Thank
you. Good night.
Thank you, sir.
Thank you. Yeah.
All the participants, I hope and I strongly believe that you have submitted the attendance and feedback form. Tomorrow we will meet by 5:45 sharp. Thank you and good night to everyone. Thank you very much, sir. Good night, sir.
Thank you.
Muthu Kumar, sir.
Thank you.
Thank you, sir. Bye, sir.